students. They may not realize it. Right. Well, we did tell them all the explanation. Yeah. The most important thing that Zoom is it records talk. We have a record. So in principle, you can record with your you think you can't make it, but then you can get it. It will be on your laptop and then upload it. I discovered a new faster way to get it today. Really, I think it chopped off 2 minutes.
Why do you need a faster way?
Because, you know,
yes.
Porridge and
Yeah.
Okay. So, welcome back. And we're really happy to be back in the Roberts building with much more oxygen. And so this morning, Europe is going to tell us about SYK approaches to eleatrical theory, on the eleatrical theory, and its possible, perhaps definite, connection with quantum gravity and holography.
Yes. Yes, thanks a lot. It's so wonderful to be here. It's such a gorgeous city to walk in the morning for half an hour. So it was great to be here. This work was done together with a number of wonderful colleagues. It started out with a paper we wrote together with Ilya Esterlis, who back then was a graduate student at Stanford. When I visited Stanford for a while, he's now a postdoc at Harvard, and we had an enormous amount of fun during what was back then something like a 5 to 6 week stay. The more recent work that will play an important role in our today's discussion was jointly with Konrad Skalm, a string theorist and particle theorist from Leiden University, and Jan Andrejenko, who's a graduate student in Karlsruhe, and issues that haven't been yet written up, but the results are there. We're done with Veronica Standier, a graduate student just beginning in Karlsruhe, wonderful student, and Davide Valentinas, the postdoc. So there will be 2 lectures, and what we will be discussing today will primarily be concerned with superconductivity in quantum critical systems, aka in strange metals, if you want so. And what we want to do as a specific side aspect of this one is to do a step-by-step derivation of what has been discussed a great deal in the literature during the last more than a decade in the condensed matter context, namely the holographic approach or gravitational approach to description of quantum critical systems. We will start out doing this in a very simple toy model in 0 dimensions, and then maybe only in the second lecture, but we will see how far we get to go on to higher dimensions. And then the second part will be concerned with much worse systems, namely systems where they're extremely incoherent. Often they're referred to as bad metals. We see what happens with superconductivity there. Good. As a warm-up, we saw some of those slides already, I think yesterday at least, in the talk by Sven, where we have where he showed, I think it was cerium palladium to silicon 2. So what we're having here is the often mentioned and connection between quantum criticality and superconductivity. We see this in such different, chemically different materials that it's something worthwhile paying attention to. It's been pointed out many years ago. Here we have the heavy fermion systems. You have a magnetic state. You somehow, in this specific case, by pressure, suppress the transition temperature, and lo and behold, right where the magnetism vanishes, we see superconductivity. This is an organic charge transfer salt, a quasi one-dimensional system, and the same behavior seems to be happening. This is an iron-based superconductor, and as we suppress the ordering temperature, we have superconducting transition temperature, largest right where the magnetism is vanishing. Quantum criticality, particularly in a slightly different version, in the so-called phosphorus doped, where you substitute arsenic by phosphorus, quantum critical behavior and transport was quite clearly been observed. So there is a connection in one way or another there. And it is a legitimate question that has already been addressed, but this is part of our discussion here, why superconductivity is so abundant. And before we go to discuss answers, let's understand the question in a little bit sharper way. So what we do here is we remind ourselves of the Cooper instability. So the Cooper instability in, say, the many-body language can be understood in the following way, that we're saying we have some quasi-particles. So that would then be captured by some finite residuum of a single pole in my single particle propagator, something that we usually results from a certain, say, Fermi liquid-like description of, say, scattering processes. And then we sum up particle-particle diagrams. In order to see what is the pairing response of the system, and in well understood limits of leading logs, there is a kind of geometric series summed up where the particle response of a single free fermion system enters. So we need to know what our propagator is. We do a little bit of a convolution. There's a log. This log, you can see, is directly related to the single pole here. So having a log then tells us that once, no matter how small the interaction, of course, this system will be superconducting. There's no way out. That is wonderful. Of course, the interaction has to be in some reasonable channel attractive, but we know how to deal with this. We get the Cooper instability. So now we can ask the question, what happens to precisely this discussion when we model in one way or another non-Fermi liquid behavior? This was done in the late 90s. Here, smart people were investigating this problem. What you do is, instead of taking the Fermi liquid pole, you just model just by hand. How would I describe a non-Fermi liquid state? There might be some power law behavior. So let's say there's a more singular power than linear. I have an exponent gamma, gamma being positive. And then now I'm doing copy paste. Let's not ask whether this is justified. Let's just do it first. I sum up those diagrams. I have to do the exact same thing, and I have to evaluate the exact same integral. Now here you recognize the Baire propagator and the self-energy correction. Now this is more singular than that term at low frequencies, but this makes the integral convergent. Hence, this is finite. In other words, now an arbitrarily small interaction would not be enough anymore to give me superconductivity. So this is just like the Stoner instability of a ferromagnet, right? they do happen. Maybe we don't have a controlled theory, but nature doesn't care about that. They do happen, but they are not the rule, they are the exception. Bardeen wrote a paper why sodium is not superconducting. There's no paper from Bardeen writing why sodium is not a ferromagnet, because it would be the exception to have, exceed that Stoner instability, particularly for that system, but also for many other systems. So therefore, this is what I meant at the beginning. Why is there superconductivity when you have quantum criticality? It seems to be that the quasi-particles are much less sharply defined objects. Hence, they don't want to pair. And of course, what we did in this analysis is that we implicitly assumed that the interaction is instantaneous. That's what we've done by just calling it a number. On the time scale of this power law behavior, this was assumed to be a constant, so it could be pulled out of the integral. And by doing so, well, we assumed it to be instantaneous. So we said there is something making the system critical, but we ignored the fact that the pairing interaction will have to worry about this fact and the retarded nature of the system in some way or another. And there are two ways that I know of, and certainly there are many more in particular when you think about one-dimensional systems, but there are two wonderful ways to think about this that have addressed this problem. So it's, to some extent, at least to some communities, a solved problem. So, and they go by superconductivity by critical bosons and holographic superconductivity. Let me briefly sketch both of them and compare them with one another. Yes?
There is something quite different between these. In a holographic case, the superconductivity is critical as well. But in the superconductivity by critical bosons, the formation of the orbital parameter actually breaks the criticality.
In both cases, once you condense, you will break the criticality. So what we are doing here is we will be, and we will get to this in some detail, but we will have to assume, and for this to work, that superconductivity is a small perturbation to some existing critical state. And there are good questions. This is not always a sensible thing to do. Very often, what you find in concrete calculations, superconductivity sets on the same scale where if you were to suppress superconductivity, criticality would switch on. In that case, you don't have a regime for negotiation. So so therefore intellectually it's sharper if you can, and you can in some cases separate these scales and then argue by adiabaticity that maybe some of these statements are still true. We will also get next lecture into the issue of what happens when you actually condense with the holographic description, at least. In that case, we will find, it's a cute work at least, that the condensation of the superconductor changes the geometry of So I'm back on Zoom.
Yes.
Yeah. Okay. So RVB is a wonderful theory. I mean, I truly love it. I've done myself certain calculations.
But it did by itself connect with quantum criticality because it was a phase of that that developed as a result of quantum, perhaps between a metal and an RVB stage, or at the edge of a box.
Yeah. No, I didn't say this. It's just too complicated for me to make this connection. Maybe put it this way. So here, so let's back to my parentage. This is what here is. There is so the fact that we don't have instantaneous. To I think in a wonderful paper from Damson when he looked at color superconductivity in due to the exchange of gapless gluons. And very shortly thereafter, there's a very beautiful paper from Artyom Abanov, Andrei Chubukov, and Sasha Finkelstein in the context of spin density wave mediated superconductivity and D-wave superconductivity. So what we have is we have some fermions and they couple to some bosons and there's some coupling constant. And this is a little bit abstract here, what I'm saying. But let's say you work hard and you convince at least a subset of your colleagues that this allows you to get some non-Fermi liquid type of single particle dynamics at some quantum critical point. In those calculations, what you find in all cases that I do know is that your pairing interaction ceases to be instantaneous. It will be a strongly retarded, singular in time or in frequency behavior. And where the same dynamics that governs the non-Fermi liquid behavior now also puts its footprint onto the retarded interaction, actually, as you see from the same exponent. It's not some exponent, it's the same exponent that enters here. So therefore the interaction, although the interaction is between less developed carriers, it is much more singular in a way that these two states really communicate with one another. These two aspects of the problem communicate to one another. And if you want so, there's almost a log back there. So in the problem, and you can get something that I would call a generalized Cooper instability in this problem.
Can you give a reason for the compensation of exponents?
We will see an explicit calculation, and then we will see it a little bit clearer. But ultimately, if it becomes very natural in the context where you this is a bosonic object. The bosonic self-energy, the bosonic dynamics is governed by fermions. And if you look at the fermion generalized singular Landau damping of the boson, if you want. So this comes from fermions, and that's why it inherits the fermionic lifetime. So it's Landau damping of the bosonic degrees of freedom. They are completely dominating the dynamics of the boson. What the boson initially wanted to do without coupling to fermions is become completely irrelevant. That's the physics underlying this one. This may not always be correct, but if this happens, that's what you find.
But you don't know of any conserving feature that maintains the long time aspect of that.
Conformal symmetry would be the right description. So that's why this pops up as out of nothing from the SYK model. Yes, Spremi. Excellent point. Of course, we will get back to some of this as we move on, but dimensionality is important and completely irrelevant here in the following sense. You need to be able to make the system quantum critical, and this, to some extent, is high energy physics of the bosonic degrees of freedom. Can you even make it critical? Suppose I have managed to accomplish this. Then there's an underlying assumption in all of these cases that the fermionic dynamics of a compressible state is local, in the sense that its frequency dependence overpowers always its momentum dependence. And if you can make that assumption, then you find this behavior. So the effective low energy dynamics appears to you zero dimensional. We will even see that this has a profound reasoning in the context of holography, where certain holographic spaces always flow to one that is local. So there's a connection we can make between these. So these are local theories in their character. The self-energy varies as function of frequency much more dramatically than as function of momentum on the Fermi surface. If you do have weak but singular corrections, then you don't quite know what to do with these theories, for example. So this is one way of looking at this problem. There's another way of looking. It's a problem that I never understood, period. And that is no sign of disrespect. It is simply something that was, the step was too big to be taken at once. So what is holographic superconductivity? It was pioneered initially by the late Steve Gubser, a gorgeous paper to read, and independently or at the same time, I don't care actually, by Sean Hartnell, Herzog, and Horowitz. Wonderful paper as well. So what do these gentlemen all say? They say there is, and we get back in the next slide onto this, there is a profound connection between critical systems and D+1 space dimension. One is space-time dimension. So D is spatial dimension, one is time, and I have a quantum field theory, and I can find a connection. There exists a connection between these quantum field theories and gravity theories in one further dimension. So in D+2 dimensions. And these gravity theories, at least in certain limits, become classical gravities. And then the strong coupling problem on the quantum field theory side can be characterized by classical gravity, which after all, being a classical theory, is something significantly more simple. And then you put a scalar field in this curved space characterized by some metric. The space is in so-called anti-de Sitter space. We get to this as well. And now I have my Ginzburg-Landau theory in anti-de Sitter space. That's what that is. That's what the holographic superconductor is. And now this problem can condense. And as this curved space to some extent mimics criticality of the system, something I haven't mentioned yet, it does. So then I have pairing in a critical state. At least what it accomplishes, it tells me how Cooper pair condensation can in principle take place in a system that is critical. So this is a different line. And now you can complain about either one of them. So, I mean, here, the usual objections that are perfectly well justified is this allowed? Is this controlled? Is there a Migdal theorem? Is this only perturbation theory? Blah, and so forth, right? All these things you can do. On the other side, you can say, is life really conformally invariant, something that is underlying this mapping? Is this relevant? What is this additional dimension in any way? And so forth.
I remember that Steve Gupta himself had serious worries about this approach. There were serious worries about the extensive entropy of n squared, if I remember, in these kinds of solutions, and at least until the Kitaya connection with this it led to a decline of interest in the area.
Yeah. And clearly, I mean, everybody who has done DMFT knows how extensive entropies can come about, right? Say in the Mott insulating state or something. That's the exact same physics here.
Right.
Yeah.
Get gobbled up by something that takes over. Like
yeah, but we are smart enough to know that it gets gobbled up. I mean, come on. Life is hard. If there's any way to make my life a little bit easier, I take it, even if it's not perfect. This is not perfect either.
But physics of metals is not physics of local moments. Local moments have a low entropy.
Yes.
Get gobbled up by the Fermi surface.
Right.
So I can completely change physics. Those were the worries at the time. Steve Gupta himself had.
Yeah, I mean, every sane person should have those worries, right? Yeah. Yeah. We will, I mean, I did not know this up until we tried to look into this, and we will see what I will do today is to give you a mapping between these two. And so one of the goal of this talk is to answer precisely this question. Yes, let's look at, So, well, these are very different theories, and depending on your taste, you may hate them both. And then you're in perfectly good situation because what I'm saying to you will now only confirm your perspective. Because if you, however, hate one of them and love the other, then you will be in trouble, because what I want to explain to you is that they're actually very, very closely connected, to some extent, just different perspectives of the same physics. To put this maybe differently in context, let me show you a picture that I took in the hallways of the Landau Institute in Chernogolovka from a person who is my absolute hero in theoretical physics, Lev Petrovich Gorkov. So when we start from a microscopic theory of superconductivity, then we have clearly in mind for conventional superconductors our BCS theory. But before already, Ginzburg and Landau were able to give us a phenomenological insight, super powerful, being able to explain such a variety of complex physics that to some extent it's completely irrelevant to the practitioner of the Ginzburg-Landau theory to know that there's an underlying BCS theory. Who cares? It's good enough to me. Why do I care, right? So therefore, for those subset of the community, it wasn't particularly important that Gorkov was able to draw direct connection between the microscopic theory and the Ginzburg-Landau theory. However, there are very, very important aspects that were revealed by Landau's ability to derive Ginzburg-Landau theory from BCS theory. For example, we know now what is the effective charge of the object that is characterized by the psi of Ginzburg and Landau's psi theory, how Ginzburg called it. And Ginzburg himself said later that they wrote in their paper that there's no good reason why E star should be different from E in Ginzburg-Landau's paper. And the reasoning for Landau's hesitation to keep it an open parameter was an interesting and a deep one, as always. And the statement was, well, if the electrical charge were to be allowed to be different, just like the effective mass, then maybe it could also be space-dependent, like the effective mass. But a space-dependent charge doesn't obey gauge invariance. And then it wouldn't make any sense. And of course, there's a topological reason underlying this factor 2 there, really, and not that we don't have in the effective mass theory, and therefore this factor 2 is perfectly allowed. And I think this alone is already deep insight and justifies all of this. So what Gorkov already also said, he also told us what is the scalar field that we have to deal with. And the scalar field is given by the equal space or equal time anomalous Green's function of the problem, where given here, of course, taken with the appropriate ensemble, so it's not vanishing, taken here, for example, in imaginary time formalism. Let's go through the arguments, because we will need this as we go along. So we have positions and time, and it's sensible to do this in the following way, that we look at center of gravity positions and time, and relative positions and time that I choose to Fourier transform. And of course, the first one, that's very important when you want to look at inhomogeneous states, at vortex physics, at what Pascal was looking at, if you want to look what happens near impurity and so forth. If you want to do non-equilibrium dynamics or collective modes of the Cooper pair, then you need to look at the center of gravity time, the frequency that belongs to it, whatever you wish. The internal structure of the Cooper pair is characterized by the relative variables. So the momentum tells us about something, or whether it's a D wave or an S wave superconductor. And the frequency tells us about the internal binding processes of the Cooper pair. That is what you see in the SDM experiment when you want to see the little wiggles where you can see the footprints or the fingerprints of the, say, the phonon or whatever binds the system in the tunneling spectra. That's this frequency, not that one, for example. So all of these variables in different contexts are important, and we will get to play with them. So what we will do, and let me just give you the answer of this talk right away. What we will do is we will start from a many-body Hamiltonian, and then we will show that there's a direct connection between this anomalous Green's function that we've just had. This is now the center of gravity and the total time, and to a new variable, and where we will see that the additional dimension that makes up the system, living in not d+1 but d+2 dimension, has something to do with the internal frequency or internal space-time, depending on whether we have a Lorentz invariant or non-Lorentz invariant system. There will be differences, and the other variables just carry over. So this internal dynamics will determine the holographic variable, and all of this scalar field then indeed does sit in an anti-de Sitter space D+2. We will recognize the metric, and by this we will then be able to make a couple of statements that the effective charge is also 2. That will not be surprising, that we have an interpretation of what this holographic dimension is and how it comes to having an origin of gravity in the system. So a few more words for us to get slowly acquainted with all of this on the holographic side of the problem. So again, I mentioned some of this already. You have a quantum field theory that lives in D+1 dimensions. And this is, of course, my caricature condensed matter physicist perspective of this. And started by a number of incredibly smart people, and carried over in the condensed matter context by equally smart people. We have a statement that the partition function of this field theory can be written down in terms of a gravity theory that lives in some extra dimension. And the way we have to look at this, we look at this from the side, and this is our extra dimension. And this is really where the curvature takes place. In this extra dimension, there's a physical statement that this variable, this additional variable, has a character of a renormalization group scale, or some, energy dependent scale, where this is the physics of the boundary, where we are in the actual field theory, and then we are flowing into the infrared. And if the system is at finer temperatures, we know that quantum critical RG flow stops, and the stop is here being provided by geometry, and there is a black hole placed there, and so forth. So that is the statement. And this sounded absolutely gorgeous to me, but it was not something that I could understand. I've seen many talks on this one, particularly in the early days, when the condensed matter community was exposed to this, and the experts in the field would always say, well, yeah, there's a dictionary. We just had that discussion yesterday with Andy, and well, the dictionary didn't help me. If I wanted to know why this dictionary is a good one. So on the superconducting side, maybe one more time, we already discussed, there is this Ginzburg-Landau theory. So this theory here then has a gravity part, maybe as a gauge part if it's charged, and there is what we will be focusing on, a scalar particle sitting in this geometry. And usually there's a statement that near black holes nothing should condense, but this is not true for these anti-de Sitter spaces. And therefore, this mass here, when it's negative and reaches a certain bound, which in the literature goes under the name of the Brighton-Lohner-Friedman bound. So there's a certain bound below which the system will then condense. So this is what was pointed out in this context. Interesting statements were made, what happens when you charge it, and so forth. So this is holographic superconductivity. So what is an anti-de Sitter space? It's always easiest to look at this, and the easiest anti-de Sitter space is ADS2. And if I use imaginary time, Euclidean time, it's even something we can look at. It's hyperboloid that I'm drawing here in 3D space, and that can, of course, be parameterized this way. And there's a very clever parametrization of these 3 coordinates, which goes under the name of the Poincare map, where I have a variable that will play this time of tau, and the variable that plays our holographic variable very naturally. And this is the mapping. You can trust me that it obeys this condition, and therefore it's a faithful, even though not complete representation of all options. And so then the geodesics in the problem are semicircles in this process. And if I draw it back on the hyperboloid, that's how it looks like. It doesn't help you a whole lot, except that it covers the hyperboloid, and that there's some symmetry broken, which makes sense because one coordinate is treated different than the others, right? The metric that comes with it has this 1 over zeta squared here. This is where all the curvature of the problem is hidden in. If it was Lorentzian time, there would just be a minus sign here in front of the time. I have imaginary time, that's why there's a plus here. If I were to have de Sitter space, which, so this is the solution of a homogeneous solution in higher dimensions of of Einstein field theories with a negative cosmological constant. If you were to take a positive cosmological constant, you have so-called de Sitter space, so you have a minus sign here. Now we are in 2 dimensions, and every reasonable book on gravity or general relativity tells you in 2 dimensions there is no, if you write down the Einstein-Hilbert action, there is nothing there. There is no gravity. What you need to do is you need to generalize gravity in a sensible way. Something that was done by Roman Jarkiv and by Teitelbaum, where you basically look at this gravity as a limit of some higher dimensional space, and you look at the 2-dimensional sector of it, and then you can still make sense of it. So we want to look at scalar fields in this anti-de Sitter space. Now I'm going from ADS2 to ADSD+2, and all I do is put the time I add in here in this case in Euclidean fashion, and otherwise if there's a minus sign in Lorentz invariant fashion, the spatial coordinates. I still have my curvature encoded in this additional dimension up front here, and that would be the metric for ADSD+2, D plus 1 plus 2, right? That's where it comes from. And if I now look at the scalar field, the one that we have written down, and you want to be concrete, then you just insert this wonderful and covariantly written version for 0 gauge field, and this is how it looks like. So you have an integral over this additional dimension that goes from 0 to infinity at t equals 0. There's the usual Matsubara sum and momenta that we all know, and then you have an action here. And this action is interesting and can actually be analyzed. And the easiest way is you just look at the equation of state or the stationary equation, which would be the Klein-Gordon equation, which is a differential equation, a second-order differential equation. That's what you get from the Euler-Lagrange equation. We will see this equation later. That's why it's good to us. You don't need to remember clearly, but this equation exists, and it's nothing that is incredibly hard for us to accomplish. Another statement is to get a little bit of a sense what's going on. Let's go to Q and omega equals 0. So let's look at static and homogeneous solutions that only live in this additional dimension. If they do so, then the rest of the problem can actually be diagonalized very, very easily. You can diagonalize the entire problem, but it takes a bit more work. And what you do is you up to a power law, you do a Fourier transform in logarithmic variables, or so-called Berlin transformation. And in these new variables, I call them psi z here, the action after a few steps takes this form. So it's basically coupled oscillators. So now we understand it. This is, say, the stiffness in the orthogonal direction, governed here by the zeta, but it's just basically the log of the Fourier transform variable. And then the mass has to be more negative than this value in order to cause an instability. And that's precisely this Brighton-Lohner-Friedman bound that I mentioned earlier. So the hyperbolic space stabilizes the system of 0 mass for a little bit longer, and you have to have exceed a negative mass in order to make the system stable. So the geometry stabilizes the state. Okay, this is mostly, I thought I'd give some more details so we're not getting so scared of these words like geometry. They're all things, all you need to do is to lock your door and take a pencil, and then this is not beyond our ability. Of course. Yeah.
At first, one specific level, critical exponent, one specific level giving something. So what happens?
No, interestingly not.
Where do different types of critical exponents?
We will see. Yeah, very good point. This is only, so this is a very good question from Ilya. He says, well, this is only if I formulate my problem in this way, I see Piers, that's very nice, but I see him anyway. So, if you are able to formulate our problem this way, the question is, does it really only describe one critical exponent, right? Characterized, say, by some power law here or so, right? And the answer is no. The mapping itself will cover an infinity. of different universal exponents that all map onto the same map action. So now the model that we want to use in order to understand the connection, I've just discussed a little bit of gravity for the reasons I just mentioned, is the Sachdev-Yekitaev model. We don't want to actually solve this model here. We need to solve a version of it that's a little bit different, but this is a useful starting point. And of course, it is a beautiful and at the same time a ridiculously simple model. So what is it? You have some flavor degrees of freedom, I from 1 to n. Think of if it are internal quantum numbers or lattice sites. It's up to your perspective. It doesn't matter. And there is some chemical potential. There's no kinetic energy. All you have is non-local interaction energy, and this interaction energy is assumed to be random. And it's an all-to-all randomness. So every site interacts with every other site, and that's why it has to be tamed, as usual, by some smallness up front, because otherwise we would have a non-extensive total energy of the system. This is a Gaussian distributed random interaction, and it has a mean squared of u squared, and a mean 0 and a mean squared of u squared, or j squared, how it's often called. So now from here, this problem is solvable. It's so simple, but it's solvable, and it's not entirely trivial in its solution. And the way you solve this is actually copy-pasting the logic that goes back to, I think, Bray and Moore in the context of the random transverse Ising model, where you do certain replicas, you introduce replicas to do the averaging, you decouple certain higher order interactions that result as a consequence of replicas, and you introduce something like bilocal fields. So you have lots of fields, but they all depend on 2 time variables. So here I've now done a shortcut. Just because it would go a little bit into another digression. But what you can do in this approach is that you write the partition function as an integral over collective fields that depend on 2 time variables. And you can then write them very neatly in a way that on the saddle point, these 2 objects that have the name G and sigma indeed become the single particle Green's function and the corresponding self-energy in OB. This is one saddle point equation, a Dyson equation. And the other one, so this is the Dyson equation here. And the other one is something that you can even write down diagrammatically as some self-consistent second order theory. So this is the effective action that you get. And if you do the saddle point of it, you get these relations, right? So we could have solved this equation before. This is second order perturbation theory of a problem with no kinetic energy, where perturbation theory truly makes no sense because the non-interacting part is 0. So therefore there are, and it depends a little bit on whether you use this as a tool to justify equations, or whether you think there's deep physics in the randomness here that gives you basically lifts frustration in the system, and allows you to have, say, non-ordered states if you were to go to lattice systems, or alternatively, there's some hidden physics behind those degrees of freedom that are random, that are soft modes that allow you to describe some physics that is otherwise not accessible, or you don't know what it really is. The beauty is these 2 equations are easy to solve. And if you make the additional assumption that this self-energy is a solution of the type that I showed you earlier, but it's more singular than linear, then it will always overpower the derivative, at least at low energies. And in this case, you can find an analytic solution. And the analytic solution is that the propagator has a power law behavior. Again, this goes back to this pioneering paper from Sachdev and Ye. There are really, really important follow-up works by Antoine Josh, Olivier Pacolet, and Subir Sachdev. And of course, there's the gravitational context was pointed out, I think, in a paper in be a branch cut singularity in my Green's function. So I want to have a non-thermal liquid state, and usually we have to work very, very hard to get this. I don't want to work very hard. Yes. Oh, the sound is gone. The sound is back. Very good. So, sorry. Yes. So this is, I looked at this as just a tool to provide me without any work a non-thermal liquid solution. Because when I saw this picture or a picture like this in a talk given in Karlsruhe by actually Dima Bagretz, who came from Cologne and gave us a talk, I asked myself, so what happens when I make this thing superconducting? Right. So here I have a normal state spectral function that's clearly wonderful and the branch cut, and I want to know what happens when this object becomes superconducting, and that led to some of our discussion. Before we go there, now already a first comment on the gravitational connection between the two, which is the following: the solution I've just given to you of these equations. Let me go back. These equations have not just the solution that I'm giving you here, but they have actually infinitely many solutions. And all these solutions can be connected in a very simple way if I take the time variable in the problem and reparameterize it to a new function of time. Then I can construct out of one solution immediately another solution if this function only has to be monotonic. Then immediately I can construct another solution. So reparameterization invariance of the problem. It's actually something that also was discussed quite intensively in the context of glasses. So this, of course, you may or may not change the boundary condition of your solution this way. And for example, this is a very, very easy tool if you want to have this zero temperature solution and you want to construct yourself a finer temperature solution, where you just make it such the new time variable has the proper boundary conditions from 0 to beta. And then immediately you define a temperature solution, construct it yourself, right? So so then you ask, well, if I've got infinitely many solutions, which one is the right one? And the answer will be given to you when you come back to this initial term here and include UV physics if you want so. At the UV scale, this term here will distinguish between different solutions and tell you which one is the right, and actually the one that's most simple at t equals 0 is exactly the right one. So, but it's UV physics that picks you the right solution. So therefore there is an energy penalty of one of those reparameterizations over another, but it's really controlled by something that would be disappearing if the upper cutoff of the theory were to vanish. So therefore, you can write down a nonlinear sigma model of all those penalties. And this nonlinear sigma model is a bit of a version that, at least to people who are not perfectly familiar with conformal field theory, is given by so-called Schwarzian derivative, a conformally invariant derivative that is an effective say nonlinear sigma model of this problem that picks the right solution at lowest energies and gives you the fluctuation expenses that you have when you reparameterize time. So why is this interesting? I mean, this is the right collective mode theory, or captures at least a significant portion of the relevant collective modes. But also the earlier mentioned gravity theory in 2 dimensions that you need to furnish with some memory of coming from higher dimensions, so-called dilaton fields, as introduced by Jacquif and Teitelbaum, has exactly the same action. So this is the quote-unquote Einstein-Hilbert action for enter the zeta space 2. It is a bit weird because it only depends on one variable, and that's because this funny gravity theory only is a surface theory. And so which is rooted in its quote-unquote topological character, right? But this is the gravity theory of an ADS2, And this is the action for the substitutive K-type model. And this, of course, has led to enormous amount of discussions and cross-fertilization between the condensed matter theory and the string theory holography community, because there is a microscopic realization of something very interesting, or there are, say, gravitational concepts that could be interesting for some of these aspects that interest us.
You write this with an explicit second spatial coordinate as well.
Yes, you can, and then you can show that after appropriate partial integrations, you get, this is a term you can't get rid of, and the other terms basically only tells you about the genus of the manifold that you're looking at in not topological terms. Yeah. Yeah.
Could you please tell us again what's going on with time here? Because last year, of course, we don't have time. Greater transmission.
Yeah. Mm-hmm.
Here, you have to write T and T prime. What happened?
Oh, these are configurations. Many of these configurations are not. So if you look, the time translation invariance as a property may be by your assumption of the saddle point, but the collective field won't necessarily be time translation invariant. The saddle point may or may not have that. Depends on which boundary conditions you place on it. So this one clearly does, but others don't have to. Here I chose one that did, indeed. Exactly, it does. It doesn't have to. Yes, very good point. Yeah. Okay, so now this is the model that we want to study. But now we already used to it a little bit. This is what now goes under the name of the Yukawa SYK model. So it is very, very simple. Again, we have these, we have added spin, but we have added spin not in any relativistically relevant way, but we just added, there is another variable that can be up or down. So in the good old fashioned matter perspective of looking at spin, we have here a chemical potential, no kinetic energy, and we add Einstein phonons to this one. The Einstein phonons have a finite mass or frequency, right? And now we let them couple phonons, whatever you want to call this boson, coupled now to these fermions with a random electron phonon interaction. That's the model that we wrote down. There's a supersymmetric gauge version that is relative to this one that was discussed earlier. Yushang Wang at Florida, at Gainesville, had, at least for the normal state, the exact same model written down. This was actually quite interesting. I was at Stanford and wrote down equations on the blackboard. And one day I come to work and somebody had written my equations on the blackboard, but it wasn't my handwriting. And it was on that day, Yushang also joined, became my office mate, and must have told his calculation to somebody. I don't even know who. And it was such a weird impression, because somebody writes it's my equations, right? He wrote the one, and this was, I mean, except for certain symbol names that were different, it was exactly the same story in the normal state. So completely independent, wonderful work. In his treatment of superconductivity, superconductivity is a higher order correction effect. That's where we differ. There's a work from Debungeon and in Eris, where they looked at purely fermionic couplings that could give superconductivity. And this model was extended to finite dimensions, and I will discuss those extensions. There's one important one from the Berkeley group. They looked at Dirac systems, where on each lattice point of the Dirac system, you have basically such a model sitting. And there's a version from Ilya and Avishkar and collaborators on compressible systems with a Fermi surface. So all what we are doing here can be generalized and was generalized, and therefore the superconductivity then was generalized by us to these situations at finite dimensions. For the time being, I stay in silly 0 dimension. So now it's technical, but we are working our way slowly forward. So these electron phonon directions are random numbers. And it actually turns out you need to think a little bit what's the right ensemble. of those random numbers. So for given k, for given phonon, this is a random matrix in single particle space. And it turns out, if I make these systems distributed in ij according to a Gaussian unitary ensemble, it breaks time reversal symmetry for every individual realization. And the implication is that the system will never be a superconductor, because time reversal symmetry broken configurations are not good for superconductivity. Alternatively, if I choose or draw these coupling constants from a Gaussian orthogonal ensemble, so they're real numbers, right? Then I get superconductivity. And because these phonons can induce superconductivity. And by this, we cooked up a distribution function where we can interpolate between the Gaussian ensemble or orthogonal and the unitary ensemble. And you can call this pair breaking. So we are titrating somewhat time reversal symmetry breaking configurations. And the reason is related to what Andrew Green was earlier asking, namely, we want to have a transition temperature that's small. And with such a parameter, I can kind of suppress my superconductivity and go to a superconducting critical point where intellectually things are clearest, and then go from there. So with this, we can just repeat what was done in the SYK model in its original fashion. We introduce replicas, we integrate out fermions, we obtain bilocal fields, but now we also get, in this specific problem, non-trivial equations and we have to introduce so-called anomalous Green's functions, so pairing fields and pairing self-energies. So there is a sufficient and a number of fields in the problem, but we've lost fear of those things, and in the end of the day, you take the saddle point. I don't bother writing down the entire action because it's just lengthy, but doesn't really tell us a whole lot. But at the saddle point, the first information that you get is you can again have a perturbative interpretation of the resulting equations and express them in diagrams, just as we've seen the second order diagram for the SYK model. And here in the large N limit, we find that the equations are just the good old-fashioned coupled Eliashberg equations. So we have a self-energy, and of course, the system has no kinetic energy. That's why it gets non-thermal liquid solutions, right? But you have at large N, these Eliashberg equations are the exact solution of the problem, whatever that entails. So you have a boson propagator that gets renormalized by fermions, and you have a fermion propagator that gets renormalized by the electron phonon coupling. These are all well-known equations to people in the superconductivity community. You have an anomalous and you have a normal Green's function, self-energy, and so forth. And then you solve this problem. You can do this analytically, and you can do this. Alpha is hidden, alpha is hidden here. Here. Sorry, that's a very good point, yes. And it's hidden here. There's a 1 minus alpha here relative to that one. Yeah. Yeah, the arrows go here in the same direction, and here they go in opposite directions. Here they go in the same direction, here they go in opposite direction. That's absolutely not visible. I have to do this better, yeah. So these are the anomalous parts, and this is the FF and the GG part, and so forth, yeah. So we can solve this problem, and let me solve it first in the superconducting, in the normal state only, to get an understanding by either ignoring superconductivity or using an ensemble where there is no superconductivity. And then you find something very, very similar. You find, from what we know from the SYK model, there is a power law solution. I just now use an exponent gamma here, mostly as in order to get the same notation that we had earlier. There is these power law solutions for the propagator of the fermions G, and for the bosons D, and well, they are singular objects. It's more maybe intuitive to see what they look like in their spectral function. There's branch cut behavior here. And here I've shown for imaginary part of D, different temperatures. At 0 temperature, it's a blue curve. It is just singular, and then temperature cuts it off and makes it and heals it. There is a low temperature regime in an actual phase diagram where we have this quantum critical phase. The reason why we have here a phase diagram is because we have two quantities of that carry unit dimension. One is the coupling constant, appropriately formulated, and the bare phonon mass. And therefore, I can therefore take the ratio and have a dimension as coupling constant. And there's a regime where the interaction is irrelevant. There's a low temperature regime where we have this power law behavior. And there's an interesting regime that we might discuss tomorrow, but not today, where we have even different behavior. So let's stay in this low temperature regime here. Another interesting aspect is, how could it be that you always get a critical solution? And the answer is that whatever you do, the fermions renormalize the phonon mass to make it completely soft. So the effective boson mass at T equals 0 is always 0. It precisely renormalizes itself to 0 in an extended regime of the phase diagram. My interpretation for this is that the compressibility of a system that isn't a non-Fermi liquid is singular. So the non-Fermi liquid solution is just a completely natural solution, and the system does everything to get there. And that implies in this case that it has to make these phonons soft. So here we would have, if you wanted, so we would have a system where electrons would make the lattice arbitrarily soft, and then we have optical phonons that have a frequency that goes to 0 as T goes to 0. And now we add superconductivity to the problem. And then there is a regime at lowest coupling constant of this dimensionless coupling constant where the superconductivity goes basically with the same behavior than what we see is the crossover temperature. That's, again, the discussion we had earlier. Here we see that superconductivity sets in when non-Fermi liquid behavior wants to set in. And that's why we have to introduce pair breaking, and this is the pair breaking curve. So with pair breaking, we can suppress the superconductivity in the system. So what we have here is a toy model as simple as possible. And the toy model allows us to get superconductivity in a mean field fashion and tune it and have superconductivity of a non-Fermi liquid, and even tune it with sufficient amount of pair breaking to a point where the superconducting transition temperature becomes arbitrarily small. And now somebody needs to tell me how much time I have left. 15 minutes. Yeah. Okay. So this is of course in its global behavior the analogous of the pair breaking curve by Abrikosov and Gorkov. TC goes down if you pair break. It has a different behavior, and it actually ends at that critical point in an essential singularity. So it ends at this point in e to the minus d over the square root of alpha minus alpha critical. Alpha critical is of order 1 here. So this is something that occurs quite often in problems that spontaneously break conformal invariants. There's actually a quite beautiful paper by, I think, Pavel Koftun and Dempson, and I'm unfair to the third collaborator because I don't remember the name. It's called Conformality Lost. And there are all kinds of scenarios by which it's been explained that this type of behavior happens when you break conformal invariants, such as a Kosterlitz-Arts transition, where this is the temperature and the flow equations are being shown to be of the same type. And this is something that happens very often in holographic models in the anti-de Sitter space ADS2. So when we saw this coming out of this model, we felt now we really need to see whether we can describe the superconductivity in a way that maybe makes direct contact to this holographic description. So you can ignore all of this if you are interested in a specific material because the model is too simple, but the technicalities or the technical aspects are easy enough so that we can make some progress and now go the next step and try to see whether we can make connection between what I talked first, the scalar field in a curved space, and these toy models. And the first statement is that you look at and this you can, near this point, I can do the following. I can go to t equals 0 and can linearize the gap equation, right? Here I can linearize the gap equation at any finite temperature, but I can go to t equals 0. and so on. And that makes it just technically easier. And if you do this, and if temperature is very, very small, I can just use it as a lower cutoff. I have a linearized gap equation. And now you see why I use those exponents. This was our earlier self-energy that made the integral so much less singular that there was no Cooper instability. And in addition, however, there is now the more singular pairing interaction. This is the boson propagator, if you want. So this is the fermion self-energy. And you see these two powers come and balance one another. And there was, so if you have a dimensionless coupling constant, and if nothing depends on cutoffs, this is essentially the only contribution you can really come up with. So this is a nice integral equation, and that is the gap equation of this SYK model. But it's an equation that is very well familiar to some people in the community because, and it was recently been in great detail studied in long and detailed papers by Chubukov and Abanov and Wu, goes under the name of the gamma model, which now explains why I use the letter gamma. So this is not just the gap equation that comes out of the silly model. It is also the gap equation that comes out of a number of problems of compressible systems that have local, by assumption or by some justification, local self-energies. And there's a long list of papers that goes over the decades where you get very similar superconductivity description than this SYK-based model would give you. In all cases, the locality there is for different reasons, but it is local and therefore only time dependent. And it is important for me because it tells me that the physics that we are capturing here is a bit more general than that of the model that we set out to capture it for. And then you have an integral equation. And at least in some limit, namely when this is the smooth function here, epsilon minus epsilon prime, if this is gamma is small, that's a very weakly dependent function, then I can essentially split the integral in two regimes where epsilon prime, the running variable, is smaller or larger than epsilon, and then treat the integrand that actually epsilon prime is large or small compared to epsilon. If you do this and you do something like 5 more steps, you can map this integral equation into a second order differential equation. And in addition, also, the integral equation tells you what the proper boundary conditions, of course, are. And so we have a second order differential equation for the anomalous self-energy in some limit. And yes. Yeah. Oh, very good point. So we did a large N theory. I should have been more precise. We have N fermions and M, like Marta, bosons. So you have, and when you do a large N, large M, you can vary the ratio. And that will vary the exponent gamma. It actually varies it between 0 and 1. And yeah, so there is, yeah, that's N equals M precisely. Yes, thank you. So we have a second order differential equation, and gamma is something that we know from the solution of the normal state. That's maybe also important to keep in mind. We have always the solution of the normal state. I assume I know my normal state. It's critical. Now I look what happens with superconductivity. Now I'm seeing the second order differential equation, and I showed you earlier another second order differential equation, namely for a scalar field in the radial direction of a scalar field in anti-de Sitter space. And well, if you have 2 second order differential equations that allegedly describe similar physics, it makes sense to check whether they can map one onto the other. And that's something that is easy. And indeed, you find if you construct a scalar field as function of a new variable zeta, and the new variable zeta is nothing else but 1 over the Matsubara frequencies of the relative time of the 2 parameters in the anomalous self-energy, and you furnish it with some exponent that is different for different universality classes. Independent of gamma, you find an equation that looks like this. Gamma only determines the mass of that scalar particle. It doesn't determine the equation. So that's where the answer to your question is. Different universality classes only give you different masses of the theory. Something I just would never have guessed. Probably people who understand this structurally deeper did. And this is indeed the anti-de Sitter 2 version of the equation of the Klein-Gordon equation, of the static Klein-Gordon equation that we looked at earlier. So this gave us a first hint that there is a connection, that we should interpret the new extra dimension as the internal structure of the Cooper pair in time-space. It happens to be 1 over the frequency. And that therefore by going into different directions in the say, bulk direction of the anti-de Sitter space, we're probing deeper and deeper the low energy physics of the Cooper pair. While this Cooper pair may still depend on other variables that we've all suppressed here, either by assumptions because it's an SYK model or by looking at, say, equilibrium solutions only. But at least we have some idea that there is a connection. So what we see is that we can make our anomalous Green's function that depends on 2 time variables. We Fourier transform this back to relative time, the one that we've just done, but we can also allow it to depend on total time. And because in our action, that's perfectly possible. And then we expand our SYK model up to Gaussian order. So there are, if you look at this for a little longer, you recognize some of the terms. These are all Gaussian terms that you can get. One is the exchange of particle-particle diagrams. Much the same what we saw in the very first or second slide, where we have to geometrically sum up these diagrams. And of course, this is the normal state inherited particle-particle propagator with the exact same less singular behavior that we have already encountered for non-Fermi liquids. But this particle-particle excitation is exposed to a retarded singular interaction that is singular and governed by the same exponent, because bosons and fermions are governed by this. It's one soup. It makes no sense anymore, really, to distinguish between the fermions and the bosons, the phonons and the electrons in this system. It's a strongly coupled state. And therefore, we have a singular pairing interaction. So this is our Gaussian theory now. We have a hunch what the map should be like. From the static Eliashberg solutions, we have the Gaussian action. So the next step is to just make an identification on the level of the action and to recover the anti-de Sitter space action. And for this, the natural guess would have been to take the same power law. I call this here Z, not zeta, for reasons that we will see right away. So we just say, well, this is now a time-dependent action. But otherwise, we take what we've just learned from the Eliashberg theory that told us that there's just a power law connecting these 2 quantities. And now I'm taking F instead of phi, and therefore the power law has a different sign, but that's not important. It's the same physics. And then you get something that looks promising, but is not the answer. It looks promising because it has a wonderful geometric interpretation. Here, I can write the action that we've just seen that looked arguably a little bit ugly. Let's look at this again. This is supposed to look ugly. Here, this action down here is condensed matter physics ugliness. And now we can write this in beautiful geometric meaning with a metric and with covariant derivatives and so forth. But the metric, unfortunately, is not our anti-de Sitter metric. It happens to be actually a de Sitter metric, right? It has a wrong sign there, and these wrong signs are all marked with minus signs. And it's even more tragic. Ignore all the holography stuff. There's a minus sign here. That means this is an unstable theory, right? It can only be rescued by proper boundary conditions on the level of the Gaussian theory or by nonlinear terms or high order derivatives, right? And it is because the boundary conditions of the problem are significant. But for the time being, we have this action and we are sad, very saddened, because we have not accomplished what we wanted to do. We have not managed to map this problem onto the anti-de Sitter space. And this is not anti-de Sitter space. This is somewhat similar to de Sitter space, and everything is bad. But then you realize that there's a group of smart people in the particle physics community that told us that there's something that goes under the name of kinematic space. The kinematic space is if you are in a certain space, let's say you're in enter de Sitter space, and you can draw an enter de Sitter space geodesics. And each geodesic can be parameterized by a set of parameters and builds its own space. And it's actually a space with its own geometry. And it turns out that our de Sitter space, the one that we live in, our SYK model lives in, is the kinematic space of the enter de Sitter space. So two events here are close if in enter de Sitter space their geodesics are close in some sense. It turns out if you use this, you can then the way you transform the fields according to this goes by what is goes under the name of a radon transformation. So you have this geodesic here parameterized by 2 points, and if I integrate the field in the enter de Sitter space over a geodesic, I get a new function that is parameterized by the geodesic, and that goes by the name of the radon transformation. We all need radon transformation when we want to reconstruct, say, our tomography picture from the X-ray tomography in the hospital. It's not geodesics; it's just straight lines, but otherwise it's a similar transformation. And if we then do this, so we add this radon transformation over these geodesics. Here, this is the geodesics semicircle. It's a simple problem. Then the new action is in fact really the enter de Sitter space. And if we do this, we do get reproduce the holographic action of a superconductor in enter de Sitter space. And everything is fine. And it's just that the radon transformation gives us fields that have much more natural boundary conditions in the UV, as we will see when we look, for example, at susceptibility. So it's not really unstable in the sense, it's a scary thing to only look at Gaussian theories without knowing what their boundary conditions are and what are the natural fields that you have to couple to them. This might be the moment when I can stop, or I can go for 3-4 minutes and I can finish it more cleanly. Yeah, is that okay? So if modulus is radon transformation, which is to some extent now a technicality, we can, and that's actually quite cute, connect all these different terms in our original quantum mechanical action to terms as in they appear in the holographic theory. So the particle-particle fluctuations give us dynamical phenomena when there are dynamical pair interactions, and this gives us the second derivative in time. The non-local interaction of the boson gives us a gradient in the radial direction, and both terms contribute to this mass. This term always comes with a positive contribution. It doesn't want superconductivity. That's what I said earlier. Superconductivity is not the natural state for a non-Fermi liquid if it has no singular interaction, which comes from this term. The second term gives us a negative contribution to the mass, which by itself, it turns out, is always more negative than the Brighton-Lohner-Friedman bound of that geometry. So itself, it wants this, and it always has to fight against that term, and therefore you can and cannot, and we can tune this with this pair breaking parameter, make it or make it not superconducting. And when the pair breaking parameter tunes it to the BF bound, then we are at the superconducting quantum critical point. All of this, the saddle point, of course, can be shown to be equal to the superconducting solution. And the maybe last comment is, this was all done at 0 temperature. If you're now willing to engage into much longer equations and technical steps, you can repeat all these calculations at finite temperatures. The beauty is, I told you, there are conformal transformations of coordinates that connect actually 0 temperature and finite temperature transformations in the SYK model. And there's a similar statement that you can make mappings of metrics at 0 temperature and at finite temperatures on the enter de Sitter site. And they actually communicate exactly on the regime where we want to these two theories to be identical. So therefore, we managed to have a little bit longer proof, but along the exact same lines, where we could show that at finite temperatures, the system that approaches the transition temperature, it's a Gaussian theory only, that approaches the transition temperature is now governed not by entity space, but by this space that puts a black hole in the entity space and has event horizon that's given by the Hawking temperature of the problem, and everything as it's supposed to be, and you get this, you get the black hole as a present of your analysis. It's not something you need to impose or put into the calculation. It is just the absolutely natural way of describing the system. And the stationary point of this one is the linearized electric equation. We also have done the phi-4 term, and there's nothing else but the square root of G U psi phi-4 term that comes out of the theory as well. If you wanted to go a little bit below the transition temperature, you can do that as well. So maybe this is a good point to stop. The message I wanted to bring across is, if you are a person who is not trained in holography and you had a tragic past of suffering through talks that you didn't understand and felt you should, there is a direct step-by-step way to understand these statements in simple models, which we could have solved otherwise anyway. So I haven't solved anything that I couldn't solve before. I will show you something maybe in the next talk where we go and use this machinery to say something new. But we have a mapping achieved, and that's what I find most interesting. We know now what this additional dimension is. The geometry is inherited from the critical state. That's why we have an entity space. A clever transformation hides the universality class and puts it into just the mass of the problem. The interpretation of the meaning is just the internal structure of the Cooper pair. So that's at least something that we can all work with, and maybe we can exploit and use or apply some of the wonderful insights obtained from this community with this additional insights. Thanks so much.
I feel I should understand.
Yes.
Is this amazing? You rewrite action in terms of these two-time functions.
Yes.
Two-time function, and then there's this amazing transformation that turns into something that looks like.
Yeah.
So, two questions. Can you help me to understand, other than recognizing this trick works? Can you give me another handle on why that does work? And secondly, if I were to try to do this for a model that doesn't have these very nice properties of the SYK model, to what extent would it succeed? And where it doesn't succeed, why not?
Mm-hmm. Well, I mean, first, the most dramatic statement was, suppose I have a good old-fashioned BCS superconductor and recoupling, right? None of this would make any sense, because we are so far from a, say, conformally invariant normal state that this is not the right language to use. If we, however, say, condense the system a little bit, right, and break the scale invariance of the critical state a little bit, then we can use this as a good starting point. So this is a very special situation. We have a critical normal state. And only if you have that, I suspect, is this really a powerful tool to talk about anything else. For example, in our phase diagram, if I now go far away from the superconducting quantum critical point, and superconductivity sets in at the scale where this criticality is showing up for the very first time, I cannot personally see that this is a wonderful language. It continues to be a wonderful language, but a useful language it may not be. Then I would just solve the problem, right? Here, it was more about conceptual insights.
If I were to net this transformation,
yes,
this transformation to this reparametrization of
yeah.
To get this triangle action, would I get non-localities in that?
Yes, indeed, you would. So maybe this is a good point to bring up one thing. The most no, that's the wrong direction. Yes. So when I said that this term gives me this is a low energy physics statement. So this is a gradient expansion of this term, and this is the leading contribution to the gradient expansion. As always, and there would be higher order gradient expansion, they would become increasingly more important then. The time derivative as well. Yeah. Both are gradient expansions. Yes. I don't know. Yeah, here's a yeah. Yeah. Yes. Yeah. No, we can condense this object. We get an order parameter expectation value in the condensed phase that you can catalyze, and then you can use the mapping backwards, and you see that you get a non-universal 2 delta over TC, but there's hidden a universal behavior in this formulation. Exactly. Everything is in there. Yeah. Which means, to some extent, something that wasn't obvious from the original formulation can be revealed this way. There is some higher universality in that model, if you want. Yeah. I don't know. Who are you? Yeah, please.
What in the problem allows you to do this transformation between DS space and ADS? Because, like, I guess usually
So,
lose some information.
This is invertible transformation. This is perfectly invertible. And all you need to you in each case you can parameterize you have a d-dimensional space, so which just happens to be d plus 2 dimensional. So you have a d plus 2 dimensional space. You can and you need to d plus 2 parameters to characterize the geodesic. They are non-intersecting curves, and that you can that non-intersectiveness is necessary in order to invert the mapping, and there's as much information in this field variable than in that one. But this is just the more natural way if you want to arrive at an antitheta space. I have not fully digested why we all not talk about this type of field, except for the fact that if I want to write down natural boundary conditions or source fields in the problem, they get much more natural in that formulation. So this is just my lack of understanding at the moment of this so-called kinematic state mapping. So there is physics maybe behind this also. There's a statement from two Japanese, I shouldn't pronounce it, that if you have something that's more complicated than ADS2, let's say at least ADS3, so we have a spatial aspect to it, or ADS4, which we will discuss tomorrow, then you want to look at the entanglement entropy of the problem. Then you would take out your region of which you want to take the entanglement entropy on your boundary field, and you find that the entropy is given by the surface of the extremal surface that goes out from this point, and is tightly related to these geodesics. So I think in this map, there must be somehow the information of entanglement of the original state encoded, which I haven't quite digested yet. But this is an ongoing discussion in the string theory community, and ongoing really 2021, 2022. Yeah. Piers, I think. Yes. Yeah.
You started out with a model which had both bosons and
yes,
both had incorrect half-step physics, and yet when the bosons disappear to in the ADS2,
where did the fermions disappear to? So what we have is, yeah, right. But I think it does make sense to look at it. So what we did here is we were looking. I'm going in the wrong direction. We were looking at the pairing anomalous propagator response to characterize superconductivity. And so we started out here with a field theory that has the normal state fermions and the normal state bosons and anomalous propagators. And our focus was to understand the superconductivity aspect of it. And that is really only in the fermions. But the entire background, the gravity comes from these two fields and their interplay. And this is the scalar field that sits in the gravitational background. But that is only made of fermionic propagators. And that's why there is a slight asymmetry, because we're looking at pairing, because the boson is not charged. Absolutely. They are present and contribute to the gravity to make it concrete. Here is the infrared component of the fermions that gives us, and here of the bosons. Those are present, and the pairing field is being fluctuating in this environment of this critical state. And that's why you have, I need to go on. That's why there's non-locality in the spatial direction happens to influence by the pairing infrared singularity. And this boson propagator is responsible for the fact that we have even a finite stiffness in the horizontal direction.
Physical particles by looking at reflection coefficients, sounding things out into the center of the black hole. And that would work for both the bosons and the fermions. So how would I recover these functions of bosons in your field?
Well, first of all, I'm not even recovering the Green's functions, the fermions. To that extent, I'm very, very symmetrical. I only ask the question, what is the pairing instability? I'm looking at holographic superconductivity. I'm not determining in the way we went about the problem. We didn't.
In that kind of theory, you could extract principle.
Oh, I can do this here as well, but I can, in the formulation that we chose, we have done this only for the pairing field. And so next lecture, I will tell you about how we obtain this pairing susceptibility. And that's precisely done this way, right? You do ink-falling boundary conditions and so forth, and you get the propagators. But we are here obsessed with superconductivity. We want to look at what happens to the pairing field as the only alive field that sits in the so-called probe limit, not changing the gravity, on top of a pre-existing gravitational background that is being provided to me by the normal state boson and fermion systems.
So you're looking at some particular part of your ADS.
Yes, a very. Yeah. So the gravitational action would consist of a gravitation. So the full action would be a gravitational theory that on a stationary point gives us some Einstein-Hilbert action and a source term given by matter fields. It would consist of, say, some gauge term if you have charges around, which we certainly have. And it would consist of a matter field term, which we chose consists of a scalar field that can condense and give me superconductivity. The full coupled problem would then check how would the gravity back react to the condensation of a particle. In the good old language, this means how does the spectral function provide opens the superconductor, right? That's gravity back reaction. We can ask the question whether there are non-linear corrections to the pairing field due to the gravitational theory. That would give us a 5-4 interaction term and so forth. What we have looked at a tiny subsection of this problem, where we didn't ask how back reaction takes place.
No, I don't.
Yeah.
I just want to see the fermions in the both.
Yeah, I think with the fermions and we are having a problem. These calculations were done because people didn't know what these fermions and the boson propagators were. We are in a much more comfortable situation. We do know this. I don't need to calculate them anymore by gravitational means. I know what they are, right? And of course, you could alternatively look how in de Sitter space fermions, boson propagators would look like, and you would get the answer that I've given you anyway. But I know this already, so I don't need to bother with this anymore. We just wanted to look at it. So this can be done, what you want me to do, but it's not something that we set out because it probably has been done many, many times by the experts in the field. There are long papers, beautifully written by the SYK community, particularly on the particle, on the string theory side. We wanted to look at the simple problem: what happens to holographic superconductivity, and can we understand it? And they're the only alive field that we allow to fluctuate was the pairing field, right? And then I can only look at its propagator. I've just chosen not to do this, but I could have done it if I wanted to. Yeah.
Thank you very much for
Mhm. Yes. 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 And at this point, I can only mean by this the dynamical dependence, because that's all we have, because we have ADS2 so far. So we have a field that only depends on 2 time variables, right? And I mean, first of all, you can ask yourselves, I have a 0-dimensional problem that has 1 time variable, right? And that's all there is. How come that I'm sitting in a 2-dimensional space? And the answer is the relevant variables are objects that depend on 2 time variables. They're correlations, right? If you want so. And then you have the total and the relative time you live in a 2-dimensional space. So the additional dimension is that you're not only caring about how something depends on total time and maybe reacts to external perturbation or an out of equilibrium, but you want to see how it depends on the relative time, something that actually we are all accustomed to when we're looking at the anomalous self-energy of an Eliashberg calculation given to us by Doug Scalapino or Bill McMillan and so forth, right? This internal structure is what I mean, that tells us how, when, at what scale do I break the pair, at what scale do I have a phonon mixing into the, and so forth. Here, the system is simpler because it's scale invariant, but that's what I mean by it. Tomorrow, we will talk about a Dirac system that lives in higher dimensional space. We will see that the holographic variable also tells us something about the angular momentum of the pairing and so forth, because then we have spatial degrees of freedom as well. Here we only have temporal degrees of freedom, and that's why it's so simple. But as a starting point to capture how we may want to think about this is quite useful. But it's only the dynamical information of the relative time, internal correlations of the pair. Thank you. I stop share, right?
Hello?
Yeah, that looks like it's showing
Yeah.
now.
Can you hear me now?
Yeah.
Okay. Yeah, it was somehow since I made audio here, it cannot.
Wow.
I don't know. Whatever.
Anyway, do you want to put up your slide again?
Okay. So now I'm just missing a pointer. But I can ask you, I guess.
Yeah. And then so just tilt this round a little bit. If you go just hand over there, so the microphone fits set up.
Oh yeah.
Better.
Well,
Just which
I don't know
direction?
where exactly, but I can talk from here. I think.
Yeah, that's good.
With the mouse because it's also better for.
Yeah, then that's
Actually,
good.
then I don't need a pointer.
Yeah, sure. Sounds good.
Yeah, well, the function of the room. Yeah, this is pure. Then you apply it to take those solutions. One time is exponentially dependent. Then you get new solutions. Yes. Now I can also solutions. Okay. And this combination here is invariant. So I should say very easy. That's you are controlling theory. Yes.
So you,
So
it's basically
introductory two times that. This way. Yeah. That's why I do these none whatsoever. And you just come from space. Yes. It coded in. Yes. Yes.
yeah.
So, and it is. I mean, clearly, yes.
Yeah. Research.
You should be able to get the principle. Yes. There must be some subtlety about how you're doing that.
Yeah. You have this
Curious, huh? It's exactly like I need
yeah.
Yeah.
They're increasingly unhappy with me.
Wow.
That's good.
Yeah, so we haven't seen you for ages, but partly it's.
Yeah, exactly, that's the reason, yeah. And now,
Well,
I don't teach it.
depending on the kind of update.
That makes it so easy. It's as hard for me to travel during and
I'm not, yeah, teaching term means less. He was saying something about the.
yeah,
March.
not gonna be one.
Okay.
But this takes a significant portion of my daily.
Okay.
So that's a sort of area.
No. But I have this, moment, it looks like
Yeah.
my kids. I was playing something very risky. So they wanted this big life that existed last. And then I had the option to say no, and it's all our fault. Or serious. And I knew I didn't really and now they really legal reasons. And now they can blame us.
Excellent.
Yes. And now they take the idea to really need us.
Yeah.
During operations.
Yeah.
So that's
Why
why
did I can
it looks like it is.
Yeah.
And then there's I know.
So I told all the way.
Yeah, I understand the rest.
Yeah, that's nice.
Currently,
I know. It's tiny little thing.
Violate all kinds of building code regulations.
I think last time it was there, it was almost.
Supply chain it's ready, but there's one which is but that
Overall, it's
yeah.
being well run.
So it's going to be very nice. It's fast.
Yeah. No.
You live on the other side and on the rainy days.
Yeah.
And so it doesn't have to stop at the grandmother's crossing.
Yeah.
You have to go straight.
Yeah.
No, you don't tell us. It's something you do, then you come to it.
Yeah, sure. You also must do. Other than just seeing it.
Right.
Yeah, me too.
Yeah, but
What's the charge to finish?
so it always looks good. Well, now you July already gets and May is still term.
Yeah. It finishes around Easter. The term after that is about.
But that, you know,
Yeah.
and it's
They still have it. Yeah. Yeah. No. Basically, you start whatever time it takes, and then the next person starts 30 minutes afterwards. So giving 5 minutes for the person to change over, that means 25 minutes. So 15 plus 10 or 20 plus 5. That's fine.
Yeah. Be able to get away from. That's something you want to do. Yeah, sure. I'll let you know. So there's a video you make that we need to work against. Yeah. It's a little bit of a conference. That's easy. Yeah. Because, I mean, people from one side. Yeah. Well, then you need to avoid school. That's. At which point do you like to become? It's fine. You know. Yeah. Okay. Remember we proposed a base diagram for it, but we still have no indication that particularly what this sort of transition might not happen. Yeah. Yeah, now got the mediation should fully work out. Okay. Anyway. It's not obvious. I thought that the minimum for both of those. Right. But it's not, it's a lot of minimum requirements that come together. Which means I think calculations is much harder than that. Right. It's not impossible, but you need to think much more carefully about how to do that. Actually, maybe one can show you. Yeah. Of course. Beautiful tool. It was really cool.
Yeah.
This meeting is being recorded.
So yeah, our next speaker is Ansgar Graf, speaking from Paris, and we're glad to continue London-Paris connection.
Thanks.
You're not sharing your screen currently.
What? But I shared it, no? So I lost it? Okay. I have to confirm that it's recorded. Okay. Well, why does it stop? It already worked. Okay, does it work now? Do you hear me? Hello? Hello? Can you hear me now?
Yes.
Okay, great.
You've lost the sharing.
But what? Why?
Go back to your slide.
Okay. Okay, so thanks, welcome everybody, and thanks for the opportunity to speak here. I'm a PhD student at LPS Orsay, and I would like to talk about a class of semi-metals that I've been studying theoretically with my supervisor, Frédéric Pichon. I will start by a short introduction to topological semi-metals, and then tell you how they are linked to what we call multiple Hopf semi-metals. I will describe some of their properties, and then in the end, I will explain you why this word Hopf why this word Hopf appears in the title of those semi-metals. And this is due to a relation to Hopf insulators. So topological semi-metals we can understand by a comparison to a simple semiconductor like gallium arsenide. If you go close to the Fermi level, you have these parabolic band edges, which are called Schrödinger fermions, and which are described by a single band effective mass Hamiltonian like this. And recently, people started to look at some different classes of materials which have these linear band crossings. Okay. Which have these linear band crossings close to the Fermi level. And And those are called Weyl fermions, and they necessitate a description in terms of a 2x2 matrix Hamiltonian. I need this, like this, with Pauli matrices. And beyond Weyl fermions, there are other classes of topological semimetals, notably Dirac fermions, which have these two superimposed Weyl cones with gamma matrices, which are Dirac matrices. And recently, people have also studied so-called unconventional fermions, which are also called chiral multifold or pseudospin S fermions, which have 3, 4, or 6-fold crossings. And experimentally confirmed are already a certain number of those materials, which you can see in this table here. Now, where's the topology in those? This is linked to Berry monopoles. So to understand this, we have to look at the Berry curvature, which is an antisymmetric tensor in the space of the momentum coordinates. And in 3D, you can write it in the form of a pseudo vector, which is a three-dimensional real vector. Now, for a Weyl fermion, which is just this crossing, you can compute the Berry curvature, which takes this form Q over Q3, which is a monopole form, and which is called a Berry monopole. And this monopole vector field is really located at this nodal point here. Now the topology is in the Chern number, which just measures the flux of this Berry curvature through a surface enclosing the nodal point. And for this Weyl fermion, it's just +/-1 for the upper and lower bands. You can play the same game for these multifold fermions. For example, with this threefold spin-like crossing, you have Chern numbers -2, 0, 2, and with a fourfold crossing, you have those Chern numbers shown here. Importantly, they are distributed antisymmetrically with respect to zero energy, which means you have this Chern number sum rule, and you have a trivial flatband in the sense that the flatband carries no Berry curvature and no Chern number. And this will be important for comparison later on. Now, we cannot have a single monopole because for the Brillouin to be periodic, there cannot be a flux through the Brillouin boundary. So for every source of Berry curvature, you also need a sink. And I want you to view this as an extended Berry dipole, which is in the Brillouin zone, which is separated by some distance or by some vector d0, which is like a dipole in this topological sense. This extended Berry dipole is responsible for non-trivial surface states of Weyl semimetals, such as the Fermi arcs. So here you have your source, and here your single of Berry curvature, and every 2D slice in between them is like a Chern insulator with edge states, which taken together form this Fermi arc here. And you also have many other unique physical properties caused by this Berry dipole, such as anomalous Hall effect, negative magnetic resistance, planar Hall effect, and peculiar Shubin of the Haas oscillations, which I will not talk about. What I want to talk about is the merging of monopoles. So if you merge two Weyl nodes, a minimal continuum model to do this is given by this Hamiltonian. So we merge them along the Z direction, and the Berry curvature can be computed like this. And now if you take this distance to 0, what you do is you annihilate the Chern numbers of the two monopoles, but so you annihilate the topology in a certain sense, but you keep an interesting quantum geometric structure in terms of the Berry curvature. So you keep this dipolar Berry curvature here emerging from this crossing point. And this crossing point, as well as the Berry curvature, are anisotropic, as you can see here, and they carry a memory of the merging direction. And the same you can do for these multifold nodes, which also gives you this kind of anisotropic Berry dipole. Now, this brings me to multifold Hopf semimetals. Namely, we can ask the question, if we can have such a Berry dipole with a linear spectrum, which is isotropic, and doesn't have this quadratic branch stemming from the merging direction. So if you try to do this with a two-band system, so you take a Weyl-like cone, you try to put this kind of Berry dipole at the nodal point, you will see that it doesn't work. Because a fully linear Hamiltonian is written like this, where the sigma I are linear combinations of Pauli matrices, and this always gives you a monopole. So two linear crossing is always a monopole. What we can do, however, is to use multi-band systems. So if I take this 3x3 matrix here, where psi is something like a valley index, you will find that the energy spectrum of this Hamiltonian has this isotropic Weyl cone and a flat band. And the Berry curvature is not monopolar, like for spin 1, pseudo spin 1 crossing, but now takes this point-like Berry dipole form, which is really located at this crossing point. So in a multi-band system, we can have a linear spectrum with this barodipole. And note that this Hamiltonian is not obtained from any merging, and this will be the main example for a continuum model for what I call a multifold Hopf semimetal. And we can already understand two words appear here: multifold because it's more than two bands, semimetal, well, it's a semimetal, and Hopf I will explain later on. So to analyze this more closely, this kind of Berry curvature has two important ingredients, which are the dipole axis and the dipole charges. Here I will always take the dipole axis along Z. So this is this axis here. And for example, for this threefold semimetal that I just showed you, if you compute the Berry curvature, you will find that these dipole charges here are given by -1, 2, and -1 for those three bands respectively. And you can, we have also models for fourfold and fivefold crossings, which always are linear and isotropic and have this kind of dipole form here with a certain distribution of dipole charges. And what is important now is that this dipole charge is distributed symmetrically with respect to zero energy, as you can see. And this obviously requires two bands, more than two bands, sorry, because in a two-band system, the Berry curvature of the conduction and valence bands are always opposite. So you cannot have this kind of behavior in a two-band system. Instead, we have this kind of sum rule in the valence or conduction band subsectors, which tells you that, for example, those two bands sum to 0, and here for a flat band, you have to take like half of the flat band for the upper and the lower sector. And notably, this attributes a strong quantum geometry to the flat band, which always kind of needs to compensate the charges of the conduction bands, because the sum of the Berry curvature of all bands still has to be 0. Now you can say, okay, funny continuum model. So what does this have to do with lattice? So let me give you some tight binding models that show this behavior. So I distinguish two classes. The first class has an even number of these barodipole crossings, which I will call a valley Hopf semimetal. And what you can do, for example, is take a 3D system consisting of these AB two-dimensional hexagonal layers, which are just graphene in this AB sector. And now you add a coupling in the AC, in the Z direction between A and C atoms, and with alternating hoppings, which gives you the sinus kz. And if you go to the low energy limit of the system, you will find that at the K and K prime points, you have these threefold barodipole crossings with opposite orientation, which are exactly described by this continuum Hamiltonian that I started with. Yes?
Sorry, for the picture of the graphene, why is there three different isn't there two sublattices?
Oh yeah, I take layers AB, and then I take an interstitial layer, which just consists of these C atoms, which are not hexagonal layer, which are like which would be a trigonal lattice, right? And then I repeat in the then I repeat the graphene layer, and I repeat this periodically in the Z direction. So I have 3 atoms per unit cell. That's why I have a 3-band system. And the second class of these Hopf semimetals has an odd number of those barodipole crossings, which I call the true Hopf semimetal, because the barodipoles cannot cancel in the sense that we will see. And those are a bit harder to realize in the tight binding model, but here's an example. So you could take a cubic lattice with 3 orbitals per side, and if you couple them in this way that is shown in this matrix, you will find that there is just a single of those threefold crossings at the gamma point. And it's again described by this continuum Hamiltonian that I showed before. Now the question is, okay, what is the physics of this kind of barodipole? Why do we think they're interesting? So first simple thing to look at are Landau levels, which I want to compare for the Hopf semimetal and for a standard Ryle semimetal. On the one hand for a single cone, and on the other hand for a pair of cones. So I apply a magnetic field, which can be tuned by this angle theta here from the dipole axis away from the dipole axis. And what you will find rather easily is this spectrum for the Landau levels, where notably here you have this cosine theta term which appears, which is nothing else than the angle between the dipole axis and the applied magnetic field. So you can really, by rotating the magnetic field, tune these Landau levels from gap to gapless and maintain the flat band because the magnetic field does not destroy the chirosymmetry. And also note that this kappa alpha here explicitly appears, this kappa alpha of the Berry curvature explicitly appears in the Landau level spectrum. And now to compare this to a Weil semimetal, for a Weil semimetal, it is well known that the Landau level spectrum for a single cone takes this form here. You have these two families of levels and a chiral Landau level, which is caused by the non-zero Chern number of the crossing point. And this Landau level spectrum is independent of theta because this cone here has a full rotation symmetry. In contrast, this single cone here does not have a full rotation symmetry because we have the specified dipole direction. And now another comparison that you can make is between this local dipole here and this extended dipole that you get from a pair of wild cones. And you can see that, of course, for a pair of wild cones, there's also a dependence on the angle between the magnetic field and the dipole direction, but the behavior is kind of distinct. So we always have this connected chiral modes originating from this, whereas for these Hopf semimetals, you don't have these chiral modes and you go from gap to gapless. A second thing that I want to show is the anomalous Hall effect. Again, I want to compare these two systems. In the electric field, anomalous Hall conductivity is just given as the Fermi C integral of the Berry curvature. And you will find for both systems very similar expressions. So here we have E cross D, here is E cross D, but again, here it's an extended dipole, and here it's a singular dipole, which does not represent the distance in momentum space. What is, however, very different is the parity of these conductivities. So as a function of the Fermi level comes from this Fermi function when I go to zero temperature. As a function of the Fermi level, the anomalous Hall conductivities of these systems have opposite parity. So for this kind of wild semimetal, you get this symmetric behavior, whereas for the Hopf semimetal, you get this odd behavior. And this parity is exactly caused by this distribution of the dipole charges. I cannot show this here, but you can show that this even distribution, in contrast to this odd distribution, determines completely this parity of this anomalous Hall signal. And finally, a third response I want to look at is weak field magnetic conductivity. So we again start with this semimetal here. We apply weak electric and magnetic fields, and we do a standard semi-classical treatment with Boltzmann equation. And you can combine this with the semi-classical equations of motion, which are here corrected by the orbital magnetic moment and the anomalous velocity caused by the Berry curvature. And you plug all of this into the current density, and this machinery gives you this important expression here, which is a current at linear order in the magnetic field, which explicitly makes appear these Berry dipole terms again. And again, this can be compared to this extended dipole from a pair of Weil nodes. And actually, all of these three expressions you can find in this current response of a pair of Weil nodes at linear order also. However, again, this D that I have here for the pair of Weil nodes is replaced by this extended pair dipole. And they are called chiral anomaly, chiromagnetic effect, and magnetochiral effect, respectively. However, here we really have this topological monopoles, and here we don't have this kind of topology, but still we get the same form for these currents. And now, importantly, this has the same form, but again, it has opposite parity as compared to the pair of Weil nodes as a function of the Fermi energy, which you can show in a lattice calculation. This you don't see in this continuum model expression. Now, finally, let me show why I call these Hopf semimetals by a relation to Hopf insulators. So to tell you about Hopf insulators, I would like to remind Chern insulators first. Chern insulators are just two-dimensional insulators without any symmetries, and the Chern number is given by the Biron-Zone integral of the Berry curvature. And this applies, for example, to the quantum Hall effect and gives rise to a so-called stable topology. In contrast, Hopf insulator is a three-dimensional insulator without any symmetry. So in your tenfold way table, you have a zero. So there's no stable topological invariant associated to these systems. But you can define a Hopf number as the third winding number of this unitary matrix that diagonalizes the Hamiltonian, just given by this integral. And well, to do this, you need to put certain constraints. You need to keep all the bands gapped. And there are certain constraints that refer to what's called delicate topology. And this is formally defined last year for this N-band Hopf insulator, but there are no concrete models known for more than two bands to study the physics. So what we find is that if we take our semimetals and we gap them, we find exactly these kinds of multi-band Hopf insulators. So we take again this semimetal with this one Berry dipole at the gamma point. we add an appropriate perturbation, which gives this insulating Hamiltonian here. And this actually represents the first lattice models for multi-band Hopf insulators. And they're rather simple because they only have nearest neighbor hoppings. There's only sines and cosines here. Whereas in the two-band Hopf insulators, you have very complicated second nearest neighbor hoppings. So to confirm that those are Hopf insulators, you can compute this Hopf number as a function of this tuning parameter here. And the flat regions are insulating regions, and the jumps are at semi-metallic points where this Hopf insulator has gap closings at some of these points here in the Brion zone. And at these gap closings, you exactly recover the Hopf semi-metal that I discussed before. This is why I call it Hopf semi-metal. So to conclude, I've shown you a class of semi-metals, which we call multifold Hopf semi-metals, which have linear band crossings with very dipole, as opposed to the linear crossings with very monopole that you have in standard topological semi-metals. I've shown you that this dipole strongly affects physics. In some sense, it's similar to a pair of wire bonds, which you could expect because there's this duality of the two dipole axes that appear. But it's also very different due to the symmetry of the kappa alpha of the dipole charges, which are distributed differently. And the name Hopf in these semimetals is due to the fact that they represent topological phase transitions between Hopf insulators. If you want to read more on this, you can go to this recent preprint. And as perspectives, I would like to mention experimental realization. We don't know about materials to probe these effects, but especially these valley Hopf semimetals with the graphene layers are very simple tight binding models, so there could be possibly something there. And you could probe these responses, for example, if you go with the Fermi level here to half filling, and then you vary the Fermi level, you will have this anti-symmetric response in the anomalous Hall effect, for example, for this Hopf semimetal, and you will have a symmetric response in a Weil semimetal. And I would also like to mention 3 papers here on ultra-cold atoms, nitrogen vacancy centers and diamonds, and superconducting qubits, all of which have studied Hamiltonians very, very similar to ours. And this is just a proposal, but those 2 are experimental realizations. So I think with the method used in those papers, it should be possible also to realize some of these models that I showed you. And other perspectives include, well, the delicate topology of the systems that I haven't really talked about, and also generalizing these bary-dipole crossings to bary-multipole crossings with octopole or quadrupole structure, and we already have some interesting results on that. So thanks for your attention.
The recording has stopped.
I have a question about the robustness versus delicacy of this. While nodes are very stable. So
yeah, so actually, as you say, the Weil nodes, they cannot be gapped because they include all the Pauli matrices already. Here,
This meeting is being recorded.
Okay. Here, the appropriate comparison is more like with graphene, I would say. So this valley Hopf semimetal that I showed you with the 2 crossings at the K and K prime points, it is not better protected than graphene. So it will be gapped by on-site potential, by spin orbit coupling, all kind of this stuff. And actually, we have looked at this a bit. You can make a whole comparison between families, these Hopf semimetals and graphene. You can add some on-site potential, which for graphene would give you the Semenoff insulator. And here we get something like a valley Hopf insulator. And you can do also for the insulating phase, this Hopf insulator I showed you is somewhat the analog of a 2D Chern insulator. So this family graphene Semenoff insulator, Haldane insulator is kind of analogous to these 3D systems that I showed you here. And they are not more robust or less robust, I would say. Yes.
So I have a couple of questions. You have discussed mainly the triple crossing. Does this discussion apply also for the 4-pole and the 5-pole?
Yes, I've done this only for gravity. So all that I showed you, Landau levels, anomalous Hall effect, and magnetic conductivity, we have done this all of this for the 3-4 and the 5-point models. You always have the same kind of phenomenology. Of course, details differ, but the Landau levels are always tunable by this orientation, and the parity for the 4 and 5-fold crossings is also the same because the Berry curvature always has the same form. and the same symmetry properties for the dipole charges.
Another question is there any symmetry requirements of this kind of dipoles in a material?
So
do you break some symmetry to be able to have both the dipole at a certain point? Does it appear at high symmetry points in the region zone always? Or?
Well, the thing is, we haven't made a full classification. We have examples, and those examples, since we wanted everything to be as isotropic and as simple as possible, so the Baire curvature and the spectrum, they're all completely isotropic, and the spectrum is linear. So what we have in the end is always, I don't know if I can go back as far, but we have always these Hamiltonians which have a chiral symmetry, actually. Or maybe I should go to the slides directly. So already the very first one I show here, it has a chiral symmetry, so it anti-commutes with the diagonal matrix, which is the chiral symmetry operator. And all examples we have always have this chiral symmetry, but I think you would get similar stuff. So how do you say this? So for the semi-metals, I think the chiral symmetry plays some important role, because you have this distribution of the dipole charges which is symmetric to zero energy, and I think this is linked to the chiral symmetry. However, for the insulating phases,
okay, that's another question I can sorry to interrupt.
How much time do we have for
Shouldn't be starting the next one.
No, you can't get a meter.
okay.
Okay, let's have to speak you for a break.
The recording has stopped.
Is there a workplace somewhere?
Yeah.
Sorry. It should be fine.
Perhaps we can talk later.
Yeah, sure.
Yeah, good. So you only need to
This meeting is being recorded.
Is the sound?
connected to the speakers. Do we need the microphone?
Okay.
Well, let's hope we can do it tomorrow.
And is there a pointer? I don't know.
It's better to use your cursor if
Yeah,
possible,
okay.
because otherwise online people won't be
Sure.
able to see it. So you need to blow up your cursor a little bit if you know how to do it.
I don't
Oh,
know how to
actually.
do it.
Are
I'm
you
not
on?
sure.
That'd be okay.
Yeah, I can try to. Okay, without mouse, it will be difficult anyway. I will.
Yeah, okay.
You are on PowerPoint or
It's a PDF.
PDF.
So-
Okay, so then yeah, okay, let's start. Or you can change the cursor on the computer. In Mac,
Yeah. Okay, then thank you to the organizers for allowing me to talk here today. I will present an ongoing project which I started recently with James LeBlanc at Memorial University, and in which we use a numerical technique, algorithmic matter integration, to study the optical conductivity in the Hubbard model. And I want to mention also the contribution of some people here in King's College in London and from University of Massachusetts that helped develop all the machinery that is behind all the results I will show you today. So I'll start by introducing algorithmic matter integration in a very simple way, starting with a very simple calculation, for example, of these diagrams, just particle hole bubble. And following the usual Feynman rules, I can give an expression to this diagram. And as I think everyone here knows, we can get rid of the Matsubara sum using simple residue theorem if we have three fermions. And we have this expression, which is just a Linhart function, where we are left with a d-dimensional integral. So the result will depend on the dimensionality of the problem. And we have our external frequency that we can continue on the real axis by using the usual analytic continuation. And this is a very easy and general setup, but it becomes much more complicated to use if we, for example, want to compute an arbitrary self-energy diagram. So here I have a ninth order diagram in which I don't think we can anyone can give an expression, but there is still a structure that we can use. In particular, we know that this diagram will have an expression in terms of product of more than 12 or Green's function, and that you can still get rid of the Matsubara sum using residue theorem multiple times. And we get a result where we have 9 times d-dimensional integrals for the internal momentum, and the external frequency appears in the denominator with some function of the dispersion, but we can still use analytic continuation to, if we want, compute result on the real frequency axis. So now, of course, there are other techniques that allow us to evaluate such a diagrammatic series. In particular, diagrammatic Monte Carlo is a very popular one. But because this technique actually stops at this stage and evaluate this integrand here, they are restricted to computation on the imaginary time or imaginary frequency axis, and which is then they need to use some numerical analytic continuation tools to get results that they can compare to experiments or others. So the idea of algorithmic Matsubara integration is really to use these simple rules that we know and that we can implement to get this analytical expression that we then integrate numerically. So the scheme is very simple. We will generate all the diagrams for a quantity that we want to compute. And we will also assign all the momentum respecting the conservation laws for momentum, spin, or energy, and so on, depending on our interaction. And then we use residue theorem iteratively to get an analytical expression for all the diagrams we started with. And we are left with an integrand that only depends on internal momentum and some external parameters such as temperature or chemical potential that we will integrate numerically. And it turns out that even for large order diagrams, the numerical integration is the more costly part of this whole process. So of course, because of the high dimensional integration space when we have a lot of internal momentum, and because of the number of diagrams, this last step is the one which will cost more computation time. And this whole process of generating analytical expression for the integrand is actually very quick. Another, just quickly, advantage to this scheme compared to the standard diagrammatic Monte Carlo is that if you have a interaction that does not depend on momentum, it only acts as a factor in front of some coefficient that is given by the sum of diagrams at a given order. So you can actually evaluate, for example, once again here, the self-energy for any value of the interaction in a single calculation of these parameters. So this technique is general, and we can use it to any diagrammatic expansion in principle, but I will here focus on the Urban model. And even more restrictive, I will focus on the 2D Urban model at half filling for everything that is left after that. And because I'm dealing with diagrammatic expansion, I just here give the interaction vertices that we will use. And all the energy scales and everything will be given in unit of t, the hopping parameter, which will be taken to 1. So now what could we compute with this AMI technique? Every quantities I can think of, at least. For example, the self-energy is maybe one of the first one can think to compute, and it has been done, for example, up to 6th order using AMI. Also, two particle quantities, so that the charge, spin, or pairing susceptibilities can be computed. And once again, it has been done to 4th order for the charge and spin susceptibility, even away from half filling and in some with some T prime parameters. And what I will be interested in here is the current correlation function, because it relates directly to the optical conductivity. So to study the optical conductivity, we'll use Kubo formula and not the Boltzmann equation that was presented just before. So in this sense, for us, in this linear response theory, the conductivity is just given by the current correlation function divided by the frequency with some imaginary factor, which means that if we want the real part of the conductivity, we will need to focus on the imaginary part of the correlation function. And this is the correlation function that we will expand in a diagrammatic series. Actually, it's this current here, average of the current operators that we will expand. And if you do this, you can, write down all the diagrams. Here I stop at 2nd order. You will find that for 3 fermions, the Leonhardt function here vanishes because we have taken a Q going to 0 limit. Same for this second diagram. And the first non-zero terms will come from this 2nd order diagrams. But if you actually evaluate them,
could you repeat it? This was too quick. Why don't we need the first diagram?
So if you have 3 fermions,
yeah,
then this will vanish because we have Q equals 0 incoming momentum, and then for finite frequency you have K and K on both fermionic lines, and this will vanish. The numerator will vanish if you write on the.
It's a scary 0, right?
For finite frequency, it's.
Oh, you're at finite frequency.
Got
it. Yes, of course. At finite frequency and Q equals 0, that's perfectly fine.
Yes, I will mention the DC limits of the 0 frequency case a bit later. So I don't focus on this right now. But
I'm always here.
So if you evaluate this 2nd order diagram that I had before, you will find that because you still have analytic contribution parameters here, your result will depend strongly on these parameters. And you can even see, if you rescale a bit your axis, that it is the only thing that controls the low frequency behavior of your results. And one of the consequences, for example, is that at 2nd order, the calculation that I've done here, conductivity will diverge. And also depends on the non-physical parameters, which is this gamma here. If you look more closely at what happens in this calculation, you will find that the dominant contribution actually comes from the self-energy inclusion in the diagrams, so diagrams of this type. And this is why we actually use the idea of bold diagrammatics.
In the previous slide,
yes,
the change omega to 0, does it commute with gamma to 0? Because I know that when you're using the Kubo formalism and working in the length gauge, for example, you can find some problems whenever you take Q to 0 and then omega to 0 or reversed.
So do you mean Q or gamma? Because you said gamma.
Ah, sorry, Q to 0, yeah.
Yeah, so as I say, Q to 0, then the two limits are not the same. So here we need to take the Q to 0 limit first, and then if you want to study the DC case, we need to take the omega going to 0 limit.
Okay, so you start from the gamma to 0 and then you take omega to 0 first.
So wait, here gamma is a small imaginary part to the frequency, so it's not the external momentum, right?
Yes, I mean, I'm wondering if we find any troubles in the computation of these two limits, omega to 0 and gamma to 0.
Actually, I have not done it because I don't expect.
Well, I mean, it must, right?
Yes.
If it depends on only an omega over gamma,
yes,
it is important whether you look at infinity or 0.
Yes.
Right? Which is.
But okay, all of this was actually just to motivate what we do next. So I have not looked exactly at, as you mentioned, the gamma going to 0 limit. Also because if the computation was well behaved, because this is finite temperature computation anyway, so if the computation was well behaved, I would expect that once gamma is much lower than all the other energy scales, which are like temperatures and so on, I should get a proper answer, which do not depend on gamma. So I don't think I did not like looked into this gamma really going to 0, right?
Some other limits when computing this subsequent activity, you can run into some serious problems, whether the limits come in or not. So
yes.
Perhaps it's worth checking.
But anyway, here I am actually not taking any of these limits. I'm not looking at the omega going to 0 limit, and I'm not looking at the gamma going to 0 limit. So the idea was then to use the idea of Ball diagrammatics, so where we can actually renormalize our electronic Green's function by including some self-energy correction. So here, an example where we truncate the series at second order. And because these diagrams has a finite imaginary part, it will regulate computation. And in this case, the current correlation is then given by what we call the skeleton series, which is the same as previously, but where we removed the self-energy inclusion to avoid the double counting and so on. And now this first diagram, the 0th order diagram, which now includes a full Green's function here, actually have a finite value. But because the self-energy itself is momentum and frequency dependent, within the AMI scheme that I described previously, it's difficult. So we use just the spectral representation for the Green's function by introducing the spectral function, which is a smooth and well-behaved function. And we now get a pole structure that is very similar to a non-interacting problem that can be dealt with with the AMI at the cost of having some extra integration variables.
So you keep those extra integration variables over real frequencies if you want so, and then but you can do then the analytic continuation in the end.
Exactly. Because so this sum over much lower sum will be done by the AMI, and we'll be left with our external frequency, which we can continue. And at low order, it's actually not that big of a deal because you can take cutoff for these integrals and so on. But at higher order, like diagrams, it becomes, because you have one extra integrals per Green's function. So it actually costs you a lot of computation time. So the process is not to compute the self-energy on a K and momentum and frequency grid. So here is an example for second order self-energy, where we can see that the imaginary part is maximum on the Fermi surface with some distinction between the nodal and antinodal part already at this low order. And once we have this, we can actually interpolate the spectral function that results. So for example, we will go from something like this at 0th order and with a broadening that is frequency and momentum dependent. shown here for this is also second order calculation. So the first thing we can check is that we now have a calculation which is independent on the numerical broadening or the analytic continuation parameter, even though we now have two of such steps. The first step is when we compute the self-energy. So here we have a analytic continuation parameter that varies in the self-energy calculation itself. And you can see that the imaginary and real part of the current correlation do not change. And also in the calculation of the conductivity or the correlation function itself, changing the imaginary part of the frequency does not change qualitatively your result. You have, of course, sharpening of some features and so on, but that's much more well behaved than what we had before. So we can now study the optical conductivity. So we did calculation for different temperatures for the current correlation, from which we extract the conductivity at finite frequency for now. And we can also look at the DC limit directly. And now, because we don't have this problem with the analytic continuation parameter, I can just take the omega going to zero limit directly. Another advantages of the AMI tool is that analytically you would rewrite the DC limit by taking the derivative of the current correlation function. But because we have an analytical expression for this quantity for the real frequency omega, we can actually take analytically the derivative and evaluate directly this expression. So I think this is what you were mentioning in the bare expansion. If you vary your analytic continuation parameter, the derivative is going to infinity, so you have something that is problematic. This is after, for you it would be, you have taken the omega going to zero limit, and then you look at the gamma going to zero limit. And no, what if you reverse the order? I'm not sure what would happen, but.
So what order did you do now?
So this, for the bare, it's also a second order calculation, and for the even there I didn't mention. Sorry, this is just the zeroth order. This is just the simple bubble.
Okay, so no vertex correction.
No.
Okay, got
it. And there's in the bold scheme, we have a well-defined answer for when the analytic continuation parameter goes to zero. So we can also study the temperature dependence of this DC conductivity, which is given here. And because, as I said, the evaluation does not depend on the interaction parameter, we can easily change the interaction and get a new answer here with a very cost-effective computation in a sense, because you just recompute the bubble in this case. If you want to study the frequency dependence of the conductivity, one popular way to do this is to rewrite the conductivity in an extended through the model form, where you include a frequency-dependent scattering time and a frequency-dependent mass normalization. And this is widely used by also people doing experiments, so it's a relevant point of trying to understand what's going on. If you do this with our calculation, we get scattering time, where I've actually included a scaling here by the temperature, because you get a nice features that at low frequency, the scattering time actually scaled with temperature. So 1 over tau scaled with 1 over t. And then you have maximum of the scattering time, which is given somewhat by the bandwidth. And the mass normalization also have some structure in frequency with a finite value at omega going to zero. Yes.
This 1 over tau is just temperature. Is it what you say?
The 1 over tau is the scattering time that enters in the conductivity.
The smallest frequency, if it's always 2 point something.
No, so okay, here it's maybe 2 point something, but it will actually depend on the interaction.
I care about it's just linear temperature.
Yes.
Is this a large temperature statement, or?
Yes. If you look at the beta, we are like above beta of 10, so it would be below beta of 10, so above temperature of 0.1, something like this. So it's still a very high temperature. It's not low temperature. But it's still okay, to me, surprising statement. And it's actually not so much a statement about the conductivity, I think, but because we, as I mentioned, we only compute the bubble diagram, it's actually a statement about the scaling of the self-energy itself, right? The scattering time should be given by the energy part of the self-energy. And if you plot the momentum integrated self-energy, you will see that you get the same scaling at omega equals 0. And overall the same. I mean, these two quantities are directly related. So now, of course, what we have done here is actually not much more evolved than what people have done before. In particular, calculating the bubble graph is what people do when they use DMFT, for example, to compute the grid function and so on. So we now have two ways of actually going further. The first one and the most interesting one would be to include vertex correction. These have been shown to be relevant and important at high temperature, and also even with form of self-energies that are very local and so on. So they are really the effect of these terms on the final conductivity is non-trivial. However, for now, because this is a recent work, I don't have data for computation of the vertex correction. It's something that is ongoing. And what I can say is that there is actually no additional conceptual hurdle to doing this. It's just a computation game because, as I mentioned, the dimension of the integral actually grows very largely, especially when you use the spectral representation form. So this is still something that is ongoing, but what we have done is to include the fourth order self-energy in the normalization of the Green function. And this is already something that could give us some interesting physics. Namely, it was shown that already at fourth order, you can get insulating behavior at the nodal or at the antinodal point, depending where you are, what is the interaction strength. And so you can get a metal to insulator transition type with a regime where the antinodal point is already has already an insulating behavior, but not the nodal point. So a crossover regime here. And just for reference, this is now something that you could not do like by yourself. Like at fourth order, there are like 12 diagrams, and this is like about 600 terms that you need to compute, analytic continue, and then evaluate. So the automation that comes with AMI and the fact that we store actually these expressions, this analytic expression is something that is important here already. So if you look at the fourth order self-energy for some range of parameters, you will see that there is actually a change of signs. And this is already something that causes us problem, mainly because here, for this value of interaction, you will still get a self-energy that is negative. So everything is well behaved. But if you actually increase interaction, you will see that at some point, the spectral function changes sign, which is here a sign that this perturbation expansion breakdown at some interaction strength.
So the reason is for this that your Monte Carlo sampling is just not respecting the causality, or why is this? Because your spectral representation should be just happy.
Yes. So the computation of the fourth order self-energy is correct in the sense. But what happens is, because you have truncated the Dyson equation, you have some value. Okay, let me say it another way. If you were to compute the full series, you will get something that is causal and that is always negative for the imagery part, for example. But because you have truncated your series, you get results that are not, you have some constellations that are missing.
I mean, which truncation do you mean? The perturbative truncation shouldn't violate causality, right?
I mean, if you truncate your self-energy expansion at some order, okay, what is important?
All diagrams of that order, I should be fine.
Yes, but then you have terms at higher orders that would cancel these contributions that are missing. And this is why at some interaction.
My hope, at least, is that perturbation theory obeys causality on each order individually. And at least that would make me much more comfortable.
So actually, I've not seen this study for the self-energy in particular, but you can find other perturbation series where the results are actually diverging order by order. And so you actually need to take all order into account to get the right results, which is a convergence of the series.
Divergence is fine, but if it's causal.
Yeah, but what I mean is because you have divergent terms, if you truncate at some point, you will have constellations that are not occurring anymore. So in this case, it's related to this causality, but I don't think it's a causality problem. I don't know if I'm clear.
Okay. I'm scared now.
But okay, one thing to keep in mind is that as long as you don't go too high in interaction, this is actually fine. This is actually more a statement of your fourth order term being larger than your second order term. So in what sense your perturbation expansion is right at this interaction value is already questionable, I think.
My suspicion is this is a numerical issue. My deep hope is this is a numerical issue of your Monte Carlo evaluation of the momentum sum or something, and not that causality at the fourth order. If you stop at fourth order, but I have never done a fourth order calculation, so I know.
Shouldn't it be causal order by order?
That's what I said. Yeah.
Oh yeah, I will actually have to look. I don't know if other calculations have been done on the real frequency axis directly. That's I'm not aware of any of other calculations. So
this suspicion collectively now is order by order, which might help you a lot identifying or improving this.
Yeah. So the main thing is here the result is the result from the Monte Carlo integration is clearly positive. So this is and the question is if there is something that is missing, it's really a part of the phase space that is not sampled at all. So it's really.
So if I chose, for example, to live on a lattice that has only two momentum points, right? Then maybe you don't need to do Monte Carlo. You can just sum. And then my hope is this is going to be just fine.
Yeah, I understand what you mean. I would actually have to look more into this. For now, I will restrict myself to the case where everything is fine anyway, which is for lower interaction strength. And once again, I compute the current correlation and the conductivity within at zeroth order, so with the bubble diagram. And I can compare this to what I had at second order, for example. And one interesting thing is that because the scattering time is actually proportional to the energy part of the self-energy, if I rescale it by the interaction, I can actually observe what is the effect of this fourth order term. And you can see that we have like an increase of scattering at low frequency, like a weight transfer from high frequency to low frequency happening here. So to summarize, what I've presented, algorithmic mathematical integration is a technique that allows for the evaluation of diagrammatic series directly in real frequency, which is, I think, the main advantages it has over other diagrammatic technique. Here I've worked with a Hubbard model and Hubbard interaction, but you can possibly include frequency and momentum-dependent interaction of vertices. If you know an analytical form for it, so that it can be treated in the same way in the AMI. And we can also use spectral representation to include self-energy directly in the electronic unit function, for example, and get some sort of bold diagrammatic expansion. On the optical conductivity in the Hubbard model, I showed that the low order perturbation expansion is controlled by the analytic condition parameter as a motivation to justify our renormalized perturbation approach, where we use a second order or fourth order self-energy to renormalize the electronic Green function, from which we get very well behaved optical conductivity at zeroth order. I've shown this breakdown of the expansion, which remains to be discussed or to be investigated, and we can extract frequency-dependent scattering time and mass renormalization, which could be used to compare to other computation. Of course, this is a ongoing work and very recent work, so there are a lot of things left to do. One thing which is our goal right now is to get the inclusion of the vertex corrections. So these second order diagrams, which would hopefully have an important impact on the conductivity and get non-trivial results. We could also extend the study of the fourth order self-energy in interaction and temperature, and to try to probe this metal insulator behavior that I mentioned. And of course, this is a 2D half-field Hubbard model, which is a very special particular case. We can extend away from half-fielding. We can include second-order hopping, and so on. Main difficulty is that the density is then a function of temperature and interaction itself. So you need to find a value of the chemical potential and so on if you want to stay at fixed density, but that's just that's not that difficult. More importantly, everything here is almost already ready to include the transverse component of the conductivity if you include magnetic field, and then you can start to address interesting questions such as this whole number or magnetoresistance and so on that have been widely studied in strongly correlated materials. And lastly, to finish, something that we are not really looking into right now, but that could be interesting. If some people know more about this, I would be happy to discuss. It's the use of force-force correlation function, which has been used to compute the current correlation function because the two are linked. But for some reason, in this bold diagrammatic scheme, the result seems very different, and we don't understand right now exactly why. And nothing that could be done, because what we have done so far is just using spectral representation, is to use another spectral function, such as one coming from the MFT or some dual fermion calculations to compare the different physics, because the MFT will lead to is a strongly coupled technique from the get-go. Thank you.
Well, we're running over time, so unless there's a very quick question.
Very quick question. How is analytic consideration done in practice?
So it's actually, let me come back. What the MI will do, it will actually compute analytically all these terms, so do all the Matsubara integration. And then you can just take your Matsubara frequency here and replace it by a real part and some imagery part, right? And you store this expression, and this will be what will be evaluated in your momentum integration afterwards. And this is also why we can take directly the derivative, for example, for the DC conductivity, because we have an analytic expression in the external frequency from which we can take the derivative and evaluate the derivative directly.
In your code, you presumably have to have a thing that knows how to convert Bose functions of energy plus the Matsubara into Fermi functions and vice versa.
Yes.
That was a code you put into the code.
Yes. Because otherwise the numerators will, if you don't do that and you do the analytic computations, the numerator will be,
crazy, yeah.
Yes. And okay, the same way, here I only have a Hubbard interaction, but you could have some bosonic propagator if you know the analytic form, and then you would get Bose function, and everything should work exactly the same, at least.
For your sampling of a momenta, do you use the same types of Monte Carlo moves that I usually use for the Hubbard model, or is it different mapping to some of these terms that we get on the slide.
Okay, that's a technical question. I'm not sure of the answer. I think the standard Monte Carlo sampling of the momentum space here, and your integrand is just because okay, there is a once you done this this step, you get so a lot of these terms, but that like the sum over numerator divided by external frequency and so on. And there is a step of trying to reduce the number of terms and all this to have a nicer integrand in some sense. But then I think the Monte Carlo sampling is done on momentum in a standard way.
I mean, these are not independent momentum, or is it, I mean, what's the kind of domains of integration?
So here I have because we have this labeling scheme that will identify the independent momentum, right? And then it will write the non-independent one as combination of the like minimum set. So all of this should be independent momentum. So you are between 0 and 2 pi.
Okay, well, it means they're all in real order.
Okay. Well, let's thank the speaker one last time. Andrew, what time do we resume? 2:30. 2:30. Okay.
Yes.
It's not really angular momentum, it's much worse.
Yeah, it's a pair density.
So, I mean, it's
Right. Now they can, I think they can, here the induced state is a pair density wave superconductor.
It's a pair density wave, exactly, but of a funny type that where there's no natural instability visible to me, which is okay.
Yeah.
But then how do you define superconductivity?
Like in a pair density wave.
It's a pair density wave, yeah.
Right, so you one translation oriented one.
What was your, sorry? It's a pair density wave. It's not due to this interaction between light and
I was just exhaling.
Yeah. And but okay, if you already put numbers on that, you have to be careful, and it's really contrary to what they came at the end. It's very small DC. So ferroelectricity that you can enhance. But something I want to spend slightly more time about is equilibrium, so ground state. So there have been a bunch of works, and people have been fighting a lot whether you can, get a non-trivial ground state by putting, for example, graphene in a magnetic field in a cavity. And by non-trivial ground state, I mean I will let you know. Spend more time later is can you get some photon condensation as a ground state, so what we call superradiance. And people have been fighting for decades whether such a phase do exist or not. So at some point in this paper, they claim that you can reach at the ultra-strong coupling regime the ground state analogous to the one occurring in the decay model with condensation of photon in the ground states. While this paper answered forget it. I mean, actually, well, graphene is still described by, it's not only Dirac fermions, you need to take into account that you have bands and it becomes quadratics. And if you include also the whole band, that won't be the case. And later, following the same logic, I mean, these people, for example, if you start with the quantum spin-hole insulator with Dirac cones, if you irradiate it, you may obtain a Chern insulator with H states, and they claim that so ground state manifold is topological with a Chern number plus or minus 1, and the photon spectral function exhibits a clear, that's not what I'm looking for, but there will be some a decay type superradiant phase transitions occurs at arbitrary weak grouping. So there will be, the H states will be emit some kind of light. It will be the ground state will be a mix of light, electron photon interaction, polaritons like, and there will be some light irradiation, so some kind of spontaneous lasing as soon as you irradiate this phase. Again, this is based on the low energy description of light matter interaction, which takes into account the dispersion relations. I suspect that if you take into account the full band description, most likely you will get different conclusion. Well, and recently there was also another example of such a superradiant non-trivial phase. So that was here was a recent paper by Mazza and George, and here they consider some excitonic insulator. So this is the phase diagram at zero temperature. You have a metal, an insulator, and you have an excitonic insulator in green here. And okay, that's a temperature axis. And they found this phase diagram as soon as you switch on light matter interactions. And they found actually that this excitonic insulator may transform and the phase associated may be enhanced to some kind of super excitonic insulator. That's what the meaning of SX, super excitonic insulator, which would correspond to a spontaneous condensation of excitons and photons in the ground states. Okay, so it's an example, theoretical example, where you will, by light matter interaction, you will, completely change your ground state and get a new phase, which is this super excitonic insulator with a spontaneous condensation of photons and excitons in the system. So, this looks quite exciting. You can really create new phase of matter by light matter interactions. And so that's something which is heavily debated these days, and with a postdoc wanting to go back and examine that in slightly more details. So let me tell you, I go back to history, what is superradiance phase transition, and so my definition of quantum phase transition due to light matter interaction is that at some point, for some critical value of light matter interaction, you get a finite macroscopic number of photons that condensate in the ground state. And this has been found in the simplest model by Dicker in 53. And Dicker considered radiating gas of single quantum mechanical system, so it will be a two-level system, still radiating, so set of dipoles, if you wish. That is described by these polymatrices sigmas. And they interact with a single mode of light. And the interactions is the dipolar light interactions between the electric field and my dipoles. So, and that's the model Dicker has been studied. And what he found actually is that there is a transitions which has been confirmed by exact calculation in the thermodynamic limit. So meaning setting the number of dipoles to infinite and the length to infinite with n over L finite. And indeed, this phase transition was found exactly, and it was found by another different language. And the idea is that you get you can solve it also by some Holstein-free Markov transform. But for GC equal h bar omega c over 2, you get your polaritonic branch exactly becomes 0. So you have an instability of your vacuum, and you start populating your ground states. So this is what is called superradiance. So you strongly couple light to matter, so here the dipoles, and at some point, for some strong enough coupling of light matter, you populate the vacuum macroscopically. Okay, and that was found for a set of two-level systems interacting with light, a set of dipoles. But very quickly, after these exact solutions of came this paper, which was, and the idea is that the role of the A squared, and read by yourself, we show that the presence of recently discovered phase transition in Dicker model is due entirely to the absence of the A squared term from the interaction Hamiltonian. And that was actually the first paper that connects where the absence of transition with the presence of the diamagnetic term. The S square term is the diamagnetic term. So means if you start with the if you install from the very start the diamagnetic term, you don't find these transitions. And that was back in the more than 50 years ago. And well, the natural equations, okay, this was done for a very simple model, dipoles. Can you extend such a study to materials? And you see that it will be, well, you need to go far beyond these Dirichlet models. Now we have open systems. And well, can you find such a super-radiant phase transitions for electronic systems? And if you happen to find it, what are the necessary conditions that you must satisfy?
So can we understand this absence? This is because the photons interact so strongly then that they just don't want to condense, or what's the upshot of the physics of this no-go theory?
Well, that's my gauge invariance.
Oh, good. Sure.
Yeah, you want an energetic argument.
Yeah.
Yeah. Here, I mean, the point, I mean, energetically, you will pay the price of a square term.
So how
it will be
so there would be an a squared term, but how would it couple to the signals? This is obvious. Or is it just?
I think
it's just by itself. It doesn't.
Yes. Yes. It's really it's an energetic balance. Yeah.
So therefore, the statement is, I don't want to condense because I have to pay.
Yes.
And this is for arbitrarily small coefficient, or is this because, as you say, gauge invariance, there's a connection between the coefficients?
It's because we have balance.
Thank you.
So let me come to that in slightly more details. There's been a long controversy about and some no-go theorem, counterexample to the no-go theorem. I mean, to make it short, so see, you have two columns. Many papers have been written on that. So, is it possible to get superradiance with electronic systems at equilibrium? So it's definitely equilibrium phenomena that I have in mind here. And people claim that for cavity QD, there is no way you can get some no-go theorem, but you may find counterexample in circuit QD. Well, the paper I just presented you, they do find a superradiant, superaxonic insulating phase, and the paper by Balazs-Dora also found it. And here they found a route towards superradiant quantum phase transitions, and here is the other column, and then some no-go theorem. And the strategy I will follow today, I will try to drive you through some this no-go theorem based on this recent paper, which is not of mine. So it's a cavity QED of strongly correlated electrons and a no-go theorem for photon condensations. So it's a recent paper, which well, is pretty by yourself. It's maybe not of easy read, but interesting. And this list is far from being exhaustive, and there have been many papers. So here are the two commandments which you may respect and you must respect. As soon as you are dealing with like matter interactions, you must honor gauge invariance first. And you should not neglect any diamagnetic term. So these are the two commandments. And so let's start with a very generic Hamiltonian kinetic term, traction term. And I would assume a single mode cavity field. It's easy to extend to a many mode cavity field. And the idea is to couple light to matter by the minimum principle. So sometimes it's a pile of substitutions. The momentum is P minus P8 times EOC. So if you do that, you will get two terms on the kinetic one. That's the parametric term. And you will get the A squared term, which is the diamagnetic term. And now you're, well, that's the Hamiltonian you need to deal with. And you ask whether could there be some phase with a macroscopic number of photons, macroscopic photon condensations. So here's the proof they follow. I'll try to give key elements. There are a few assumptions behind this proof. No relativistic effects, so no spin orbit coupling, all that. And they need to assume, actually they can prove that it's exact in thermodynamic, a separability of the ground states. So the ground state is a tensor product of matter times light. So the first thing you do, you get rid of the diamantic term by a Bogomolov transform. So here, notice that all this Hamiltonian is quadratic in the photon field. So you can always do that by a Bogomolov transform, and that's the form of the Hamiltonian you obtain. The price you pay, you modify slightly your light matter interactions by this coefficient lambda, which is related to the diametric. Delta is related to the diametric coefficient, so basically these two factors. And you modify the cavity, you get an effective cavity frequency, which is modified slightly. And then you calculate the parametric current operator, which is just the variation of dH over dA for A0 equals 0. So you get, that's how you get the parametric current operator. And what you want an effective photon Hamiltonian. So you take the average of this Hamiltonian with respect to the matter ground state. And then you're asking, could there be, let's assume there could be photon condensations. So it means a current state of photons. So you will assume that your photonic ground states, you will replace it by a current state. Current state is defined by eigenstate of the annihilation operator. Okay. Fine. And you will calculate your ground state energy of your effective Hamiltonian. So you have taken the expectation with respect to the electronic ground state times some current states, photonic ground states. And it's easy to calculate this ground state energy. And you find, minimize it with respect to beta, and for that, you assume it to be a current state, so beta will be basically C numbers. And you find the value that minimizes your energy. And if you want photons to condense, for that, it must be energetically favorable, so you want the energy each side for this specific current state to be smaller than the absence of photons. And if you plug that in, it means that you need to satisfy this inequality. It's a non-trivial inequality because beta bar and psi are still connected to each other. So, in other words, I just rewrite the same inequality as before, and then you use the Stisneff theorem, which allows you to write a linear response. So you assume this that the average expectation value of H minus expectation value of H with respect to psi 0 is in beta squared. And the coefficient is related to the susceptibility, the parametric current susceptibility. So it allows you to, if you plug that in, it will have inequalities relating the susceptibility, the parametric current susceptibility to these lambda and beta squared. So if you plug that in, that's the inequality you find. You must satisfy this inequality for photon condensation to occur. So again, this is the paramagnetic current response function in the Lehmann representation. That must be larger than the photon condensation, and this is the diamagnetic term. But the point is that you must satisfy gauge invariant to your systems. And if you take a physical system, and assume some uniform mode, so the Q equals 0 limit, static, we have already been considering. Well, there is no this physical system cannot answer to change of vector potential because you can always gauge out the vector potential, so there is no dependence on it. So and this gives you some strong sum rule, which is called Thomas-Reich-Kuhn sum rule or F sum rule. This gauge invariance actually relates the diamagnetic contribution to the constraint, the diamagnetic contribution and the parametric contributions. And this gauge invariance basically tells you that the diamagnetic must compensate the parametric term. So in other words, the parametric term, which is here, must be exactly compensated by the diamagnetic term. And this is a consequence of gauge invariance in your system. And well, if you impose this equality, but if you gauge invariance impose this equality, then you are back to 0 larger than h bar omega c, which is obviously cannot be satisfied. So therefore, based on these few assumptions, it tells you that gauge invariance excludes photon condensation in a uniform and static electromagnetic cavity field. So omega to 0 and q to 0 limit. So this phase, all these exotic phase which have been found, at least most of them violate gauge invariance. So, and it's very easy to violate gauge invariance. I mean, but this thing, no. As soon as you take a continuum limit Hamiltonian, like you linearize your spectrum around zero at point, you forget about all the higher bands, and when you do that, you replace P, which is by P minus EA, and you get only linear terms. There is no way you get A squared term. Actually, the A squared terms, if you take the real band into account, there are higher bands, which are quadratics and all that, and the A squared term will be restored. But if you only, let's say, if you project your matter at low energy, switch on light matter interaction and do your stuff, you will get this exotic phase, but they are wrong because
so one of the assumptions was that these two subspaces were separable. If my ground state of the electronic system, the absence of the light matter interaction was degenerate, so even twofold degenerate, right? Nothing fancy. So then there is a symmetry which I could continuously break, but then I also would expect that the actual ground state would be in some way an entangled state.
Yeah.
Can this help me?
That may help, and this is actually, that's one of the assumptions. They assume the ground state to be well defined. Yeah, if the ground state is mainly.
But even doubly degenerate, right?
Yeah, yeah.
Not a big deal.
That may, it's a good point. Yeah, that may help you. Will it be enough? I don't think that. I have not seen a proof extending to that direction, but that's a very good point actually. They are trying to. I mean, I discussed with Polini. That's something they are thinking about. I think that the question is open.
Surely a classical electromagnetic field is a kind of complex, right?
Yes.
It's a macroscopic number in some sense. So I mean that's a proof of principle, it's just a proof of practice. Not one.
Sorry, what is your point? Sorry, is it related to?
I don't know. I'm just when you have a no-go theorem, it seems to fly in the face of the fact that we live with physical static classical electric field.
Yeah, sure, but right? So here these no-go theorems I put some material in just in a cavity, and there won't be any. I mean, it won't laze for free just by switching on a cookie. That's what it states. Sure. So, are they? I mean, that's based on these few assumptions. Okay, this is exact, and that's well. You have to work on the details, but that's not. I mean, it's a linear response and nothing more. I mean, that's it. So obviously, the question: can equilibrium superradiance or photon condensations be arise in nature? And I try to convince you, yes, that the answer is positive. And well, that's one option. Best way to do the metamaterial, the Ivanov singularity, and that's my answer at least. But I will try to drive you through this answer in slightly more details. And well, obviously, we need to circumvent this no-go theorem. And this no-go theorem was based on a Q equals 0, purely static. So the most naive way to circumvent the theorem, how about finite Q? So, and a possible route to circumvent this no-go theorem actually was first considered in that recent paper by Pasco and collaborators. And then they look at cavity QED for 2D electron gas in the presence of Rausch-Bas spin-orbit coupling in a perpendicular static magnetic field. And they look at Landau level crossings, and they did found some superradiant at finite Q. So we wanted to consider instead of very simple systems and see whether we can find elementary candidates that would allow for superradiance. So this is the list of questions, and we try to, I think, bring some answers to them. So what is the general criterion to find superradiance with spatially modulated cavity modes? Where and how to guarantee gauge invariance, which is somewhat non-trivial, and characterize the properties of the superradiant phase. And that's these last parts we'd like to spend slightly more time. Let me first answer to the third questions. To avoid problem with gauge invariance, well, we work on the lattice. No low energy Hamiltonian, let's stick on the lattice. And typically, the Hamiltonian I will be considering is lattice, a tight banding Hamiltonian, quadratic, and eventually I can consider some local density-density interactions. Okay, that's for the electronic part. How about the light matter interactions? Well, I just do some Pyrus substitutions in the Coulomb gauge. So, meaning I replace my OPIN parameter by a dress OPIN, and this lambda here becomes just a phase, which is the interval when I go from RG alpha to RG beta plus, when I go from position G alpha, orbital alpha, to position G orbital beta plus delta. And that's the potential thing. Okay, so that's what we learned. Quantum mechanics, just Pyrus substitution. So if you expand now your Hamiltonian, you will find a linear term, which is in A, and that will couple to the parity current. And the second term will be the diamagnetic term when you go to second order in the phase expansion. I wrote it in Q space and Fourier space, and that's how there is. So actually on the lattice, the diamagnetic term is quite ugly, but I won't show it. And so you have this electron-photon coupling, which I rewrite here. I will assume a single cavity, finite Q cavity mode, just this mode. And the onset of superradiance would be some ground state instability. So you hope to get some photon condensations for some value of the expectation, for some expectation value of AQ. And again, I will have in mind some current states. So that's what I have in mind. There will be some alpha Q bar, which will signal the onset of superradiance. Okay, you have to work out the algebra, so there are many ways to do it. So for example, for this to happen, you need to have the second derivative of the ground state energy with respect to alpha Q to be negative. And this, actually, we found after some lengthy calculations using linear response and angle stiffness theorem, we found that this inequality must be satisfied. And here, the key ingredients is the total current susceptibility and the energy of the cavity. Well, I just rewrite it in a way. So first, if you send Q to 0, then you know that, again, the total current susceptibility must be 0 because there is an exact cancellation of the parametric and diamagnetic state. So this guy must be 0. And again, you find the same inequality as before, 0 larger than 1, which is not possible. So we recover this no-go theorem, but here which is as expected. And we found something else, also in the process, then we found that actually there is another sum rule, which is called the F sum rule, for the longitudinal susceptibility, which must be 0. So in the directions parallel to the potential vector, to the direction, means there is no way to get superradiance. So it means that in the 1D system, even interacting as you wish, you won't find any superradiance at finite Q, not only at Q. So that's an extension of this noble theorem. There isn't. However, in the transverse directions, we do have room to satisfy this inequality. So let me inspect into this transverse susceptibility. There is two contributions, a parametric contributions, which is negative, and a diamantic contribution, which is positive. And okay, what does it mean? This epsilon mk and epsilon mk plus q is a particle Hall excitations. So this is a dipole matrix element. It's a particle Hall excitations in your system. And ideally, if you want to find some the negative contribution, the parametric contribution to dominate, where compared to the diamantic one, if this term happens to be diverging, then you're in business. So what we will, let's push to the extremes. Let's assume that we have some diverging parametric contributions, and then we know that this inequality will be satisfied. And remember, chi is negative, there is -1 in front of it, then you are sure to find some diverging quantity larger than 1. So if we are looking for conditions to get the diverging parametric contributions, actually, just by inspections, we found that there are actually, we found two ways for this quantity to diverge. First, when we do have some nesting conditions, so when you have two lines of Fermi points connected by finite Q, Q is fixed here. However, or to have a diverging density of states at the Fermi points, so kind of Van Hoff singularity. And this will be, we found some, for example, for quadratic or higher band touching. I will show you some example where this can actually give you some log divergence. So let's start with a very simple model with perfect nesting. 2D electron on a square lattice at alpha. Then the Fermi surface is the square. And suppose I will consider a finite Q, which connect, for example, the two edges of this square. So a pi. So pi over A, pi over A. Then you can, it's electron on a square lattice, you can exactly calculate your parametric response, and you will find that it's indeed, at the endpoint, it's diverging logarithmically. And so at finite temperature, the log will be cut off, but you find some diverging susceptibility parametric contributions. So in other words, it tells me that below some temperature, Tc, which is unfortunately exponentially small, this term will be diverging and dominating and will lead to the superradiant phase. So, okay, let's forget the numbers, but let's stick on 0 temperature. And so this example tells me that if I go to an outflow temperature, I will get a superradiant phase at finite Q. And how could what would be the shape? What would be the properties of such a superradiant phase? So it means now that I decorate my open parameter by some phase. And actually, in the superradiant phase, you will get open parameter which are now phase dependent along some specific directions. And what you realize is that the ground states will acquire a finite occupation number. So you have a spontaneous time reversal symmetry breaking, and you have finite flux now. So the total flux through my well, you double my unit cell, and the total flux will be 0, but you will get a staggered pi flux phase, and this phase now will have some Dirac cones, and you can I mean, actually, you know what this phase is. You can calculate this. There will be some spontaneous magnetization, which is exactly the one I wrote. So you have it's a staggered flux phase, which was actually studied by some quantum model by Affleck and Marston some long time ago. But here, this spontaneous symmetry breaking realizes naturally a staggered flux phase. And despite I started with a simple tight banding model on a square lattice, and just by there will be by the spontaneous flux, I will get non-trivial protected Dirac cones and very natural Berry phase. So yes.
I'm just probably not following properly, but to get something at such a momentum Q star, don't you have to think about the energy of the photons at having C times Q star, or does it not matter?
First, Q star, I mean, we're talking about pi over A, so you see that it's a huge Q.
Yeah.
So it's pretty unrealistic.
So how are you going to do it?
That's a toy model. It will come afterwards. Yeah, that's it. On the toy model you can do it, but if you think
you have to have a medium and
yeah, I mean, so yeah,
way down.
So yeah, I mean, if you think twice, you see, look, A pi over A, there's no way to work. So typically, I mean, for sure, light matter interaction does not. I mean, the fact that the vacuum permittivity is a small number does not help you. And what you will need is the typical matter length scale be much larger compared to the typical cavity length scale. So here the matter length scale is the angstrom. The cavity with angstrom, you forget it. So you need this. In my proposal, you will need most likely metamaterials. That to be honest, most realistic. That's what I would. Or I will show you some other example. You need to. Van Hoff singularities might be also promising, you know, but again, still, you will have to face the cavity typical length scale, the transverse cavity length scale, to the typical matter length scale. So you need to make an effective A much larger. Okay, that we can discuss. So that's the second toy model. And electrons on the 2D honeycomb lattice. But it's a toy model, so we are looking for systems with Van Hoff singularities, and we found, I mean, because of colleagues who study that model next door, so we pick up that model. So it's honeycomb lattice, but with third nearest neighbor, T and T3. So that's T3. And you assume that this T3 can be fine-tuned to T over 2, and for this very specific value, actually, you have the Dirac cones now becomes parabolic band touching at K and K prime, so which are sketched here. And what we will consider is that Q will now connect these two parabolic band touching. So again, I'm talking about something of the order of the distance between the two Dirac cones, so it's very large Q. And for this very specific model, you can show that. So basically, nearby you can linearize your spectrum. So it's a particle or excitations. So you replace that by some k squared minus k plus q squared, and you get it's integral. You will get a log divergency for this integral, and this numerator is finite. So you get again a log divergency at the k points or the k prime. So it means that if you go to at zero temperature, you have a diverging parametric susceptibility that it needs to be cut off by going to finite temperature. So we know that at zero temperature, this toy model will exhibit some super radiant phase transition at finite Q, and the Q here is the one that connects the two Dirac points. And the funny thing is that, again, let's describe the super radiant phase transition, and you get again the staggered flux phase, which spontaneously breaks time reversal symmetry. So you know your brilliant zone is replaced by a mini brilliant zone divided by 3 or extended by factor 3 Euro space. And you can check that you have the total flux through the unit cell. The new unit cell is now 0. And what you find that way is a variant of the Haldane model for the superradium. So here, this is pretty interesting, is that despite you start with something rather, well, you start with a band touching Dirac-Hamiltonian with a quadratic band touching, and just by coupling it light, you get some gap opening, and what you found is actually a Chern insulator by light matter interactions. So this Chern insulator, if I diagonalize it on a ribbon geometry, I will find H states here, and these are my H states, which are actually a mix of electrons and photons. And I think that's I found it's a cute example, still completely toy modelish, I agree, where you find an equilibrium topological phase transition by switching on light matter interactions. And this is you need to go to pretty strong coupling. You can study the properties of these H states and calculate the Chern numbers. And this is the 3 lowest superradiant states with non-zero Chern number. Okay, so that's what I wanted to say concerning toy models. But how about real life? Can I go beyond toy model? And clearly, the ingredient was to have a huge parametric contribution compared to diamantic contributions. Actually, in a recent paper, Andoliner worked out these. After some manipulation of these inequality, they found that actually for 3D cavity, you can rewrite the superradiant criterion in a much simpler form involving what we call the orbital susceptibility. Basically, in 3D, you need the orbital susceptibility to be larger than 1/4 pi. And the orbital susceptibility is the response to some magnetic field, finite Q magnetic field. It's a thermodynamic response. So it means we are looking for materials with a strong orbital susceptibility. That tells you which direction to find. But actually, in real life, free fermions they expect diamagnetism and not paramagnetism. So we need some orbital paramagnetism, while in nature, diamagnetism is more common. There are ways out. People have found it in dot graphene sheets, but and you can find also it in graphene from DR to paramagnetism, but still it's small paramagnetism. This paper plays an important role. Vignale argued already 30 years ago that you may have chance to find orbital paramagnetism provided you look for Vanov singularity. We found it by inspection, but it's actually a general criterion to find some, to look for paramagnetism nearby Vanov singularity. So that's a calculation we did recently. Actually, there is a system which is known to exhibit Vanov singularities, the twisted bilayer graphene. And at pretty large twist angle, it's 2.8 degrees, for example, we did calculate the orbital susceptibility and found some, dominating parametric orbital susceptibility, which is pretty large compared to the spin susceptibility, for example, but still, it's dimensionless unit. Remember, I need to be larger than 4 pi, and these are very, very, very small numbers, and several orders of magnitude too small to reach superradiance. So even in real material twisted by layers, you may find it outless. The idea is that here, in this moiré pattern, the effective matter length scale is much larger. You can compare to, it's about the Brownian zone is typically 100 times larger than the Youngstrom, typical limit cell. But totally, it's very dilute. Still, it's too small to reach a superradiance. So, or maybe some, I mean, in this recent PRL, they advocate crossing between Landau levels. But if you look at the superior instability, it does exist. But if you look at numbers now, they found it. You need an extreme fine-tuning of your magnetic field up to 4 digits. It's 0.1237, 0.1237, so 5 or 10, 6 digits of fine-tuning. So there is no way you can reach so much fine-tuning, whatever disorder we get it. So it looks a bit disappointing. I mean, this phase does exist, this phase, but demands huge fine-tuning. So well, I think maybe metamaterials offer one way out, and with that, I would like to summarize. So at least this superevent instability takes place at finite wave vector. It does exist, but unfortunately, the coupling is too very small, and the conditions for it to be reachable, you need matter to match this 1/2. And for realistic cavity, which is a transverse cavity, cavity is something physical. It has at least a micrometer or maybe 100 nanometers typical size. Well, that's really metamaterials, I think. Otherwise, pretty much hopeless. And I repeat, okay, that's so bad, copy paste. So that's my message. There was something else I wanted to. So, and with that, I would like to conclude. And let's hope for metamaterials and superradiance with genuine materials seems still dream today. We need a very good idea. Thank you for your attention.
About the high-flex lattice, in my understanding, don't actually break down versus flex plus pi minus.
Yeah, but still, you have no total flux is 0, but still you have some. It's like the Aldane phase. You do break down versus.
Right, but I mean, it's a bit academic to say whether the flex is positive pi or negative pi.
No, but it's an alternation here.
You can always insert integer flex. It's just a gauge transform. Now the question is, are you allowed to gauge transforms here, or are you not? I mean, you can write down the real Hamiltonian.
Yeah, but we did write it really. It's not a total. It's a non-uniform gauge transform, and it's alternating flux. So pi minus alternating. It's like in the Aldane phase. It's a pi flux phase. It's called in the literature.
So I mean, the question is, are you sensitive to the gauge in all space, not just in the lattice position, so to the degree that those two things are distinct? But as far as the lattice is concerned, the two are actually the same. But if you start from pi substitution, then you can only define flexibility with pi with pi substitution. So what's the interaction? Second pi flex analysis equal to the homogeneous flex.
I don't think I agree. I cannot gauge away this staggered.
Unless you have a continuum potential in continuous space. You only consider it on the lattice.
You can get it away. You can put it at the border, maybe. Or...
No, I mean, you can write down Hamiltonian, which is real, and which has a vector spectrum.
But the thing is that pi flux phase is equivalent to no phase at all, which.
No, that's not true. No, you double the units.
Yeah.
You can't distinguish positive and negative.
Ah.
It doesn't break versus my count.
Same as 90 for magnets.
Yeah, it breaks.
No. Well, you have to translate by one. You don't get close to the nodes.
Yeah, I mean, we probably distribute phase symmetrically to all four links. You don't have to do that. We put it on just one link. And we return each. Except that
here that
your calculation is a continuous variable, and
no, it's not working the lattice. There is a finite q pi pi, so this pi pi reprogram this direction is in. Let's see.
Written down the Hamiltonian five-flex status.
This is dispersion relation. There's no way to.
Well, I mean, the thing is, the dispersion relationship depends on the gauge.
Yeah.
So you can just map this dispersion relationship to certain different shapes.
And the key here that I do get these Dirac cones which are very protected.
Yeah, I know the Dirac ones, they're there.
There's no way out.
Right.
And so you'd be claiming there would be no spontaneous current for magnetization.
Well, that's not.
The total magnetization is zero. That is fine.
And the current.
I know, yeah. Okay. I even know loop currents.
That's true. Yeah, the statement rate, the Hamiltonian.
No, I've loop currents. I mean, inside plus. If you consider this loop, it's zero. And I can.
All right. Yeah. Okay. So you say the expectation value of KFR influence space.
Exactly. That's my statement.
What would happen if you put something like a particle crystal in your cavity? Would this somehow improve your problem, or can you think?
I can let you answer the questions.
Or how is the periodicity important, except for simplifying the problem inside this?
I mean, here we reach this superior. I mean, because with this, in that case, we're nesting. So I mean, basically, the many processes which connect to and I would say that this works the other way around. Because the crystal is more open to the grand surface. It could be dilute and no way. I would say that. So it's. I think it will be a diametric response that we eliminate. But I don't know what is the orbital susceptibility of the principle.
Yeah, exactly.
I suspect it to be diametric, mainly. No. But I mean, if you want to retain something, low energy Hamiltonians, I mean, if you are interested in light matter interaction, many people are, on your gauge invariance. Because working with low energy Hamiltonian, as you like to do, and switch, I mean, white light matter coupling is dangerous fix. Because you start with something that violates gauge invariance, and you may find all the crazy things you like that are trustworthy. And so it means that we raise a few issues. If you want to, for example, I mean, there is the idea these days to combine DFT and structure, and incorporating light matter coupling at the heart of DFT. It's not so easy. I mean, how you make sure that you guarantee gauge invariance? That's not easy. At least the proposal we would like to follow is, okay, do the DFT calculation with light matter, we find the Vanier web functions, we go on the lattice, and then we switch on light matter cooking. Is it equivalent to finding a way of incorporating light matter interaction at the level of DFT? Do we find the same physics? I don't know. This is a pretty open question. And this issue about gauging variance, all that is not only crucial for this exotic phase, but if you want to, look at finding enhancements of superconductivity, all that, that's something we really need to be careful about. Especially if you want to go to strong light matter cooking. So I see that.
If I go into a superconductor, the photon gets a mass. Can I then avoid all of this trouble?
What problem are you referring to?
Huh?
Difficulty with gauging variance?
Yes. Well, let me rephrase it. I go into a material with a highly singular dielectric function.
Yes.
Which is maybe a more mild way of saying something. And so therefore, my actual photon propagator, because it sits in a complicated environment, maybe this is so general that you can't get away from it, but here the photons are always taken as God-given and untouched. But we do know in many materials they do change the property significantly. And the photon propagator, while propagation looks very, very different from the single mode description that we use. Is there any way to get back into the game? And superconductor is just the craziest version of it.
Yeah.
Isn't that
that's the thing? That's correct.
And I've heard that most of the main advances in the area of photonics, where you're not really dealing with, you say, dealing with metal materials, you're not dealing with electronic materials per se. But then, of course, you don't have fermions in the same sense. The photons in general. Now, the interaction with quantum fields. Isn't the fact that the sea is so extraordinarily large, don't be something that in practice means you have to think about something where the energy scales and wavelengths are more ideally matched?
Exactly, that's what metamaterials might be the only way to do this.
To rephrase the statement, I mean, I think there's some connection between these comments. I mean, suppose I am in a metamaterial, my artificial pattern couples to the light in some subtle way that we don't even want to understand. But it does look very different from the minimal coupling that you do when you couple to the negative electron, which is nothing else but saying that's a complicated dielectric function.
Exactly.
Right?
That's I think that's where I would more or less re-explore. What I learned from that is the conventional way, let's forget it. And if you put numbers really out by orders, so I would explore more on the material level.
Right.
Cavity, look, we do know cavity with 1 micron thickness, maybe even less. You won't never do an unstream cavity. So the only way to operate on the material and look at non-trivial, I fully agree. So for this community, forget superradiance. However, well, still, we may manipulate a little bit, and these days, some people want some huge enhancement of superconductivity. We are far from equilibrium. You already send a laser to you, you almost destroy the sample, so God knows what you're doing. Check the directly so plastically. So it's far from an equilibrium well-behaved medium. But I can understand that to be ready to system for every year, you may enhance some specific funnels, and therefore enhance the TC. So that is cavity funnel engineering might be an interesting way to at least manipulate the superating temperature. It's more all the planetary. That's something which is, I think we see more progress in the years to come. Wow. The heat wave also is in London.
Isn't a semiconductor laser in some sense an example of something where you've got a coherent combination of an electronic medium and the electromagnetic medium? You've got a continuously operating solid state laser. That surely is an example of a coherent state of radiation that's coexisting and interacting very strongly with the fermionic system, which is driven. Another example of in a cavity, you can keep it there, you can boost its intensity. So I guess I wasn't really sure at the beginning what super radiance really meant, actually, whether that was.
Super is equilibrium for synchronization, not driven. Relays for free. To be clear, I mean, super radiance has never been observed. So therapy, for the moment, it's just theoretical things. But driven is okay.
What is the difference between that and the subject of time resistance we heard about recently? Isn't it really the same thing? It's not static.
Yeah.
Then it creates the version of the time crystal. It is static, just static electric and magnetic fields.
Yes.
Can have. Right, so you wouldn't call that super radiant. So isn't the super radiant state in where you're applying radiance after time crystal? A ground state which spontaneously breaks time. Yes. Time translation state. Or was it supposed to be a state that didn't break time? If it had a macroscopic field at the time, it would be an example of a time crystal. So it's subject to all of the no-go theorems that were advanced there too.
Yeah, I was in omega to 0 limit, so your time crystal will be escaped.
You don't want to be omega equal to it, or you do?
No, the proof I provide was omega equals 0. So if you allow omega finite,
omega equals 0 is a static electric field.
Yes.
You know? But every crystal has got static electric, spontaneously formed static electric fields.
Photons instead of finite frequency.
But
that expectation
Expectation
of
value.
that system then is supposed to be time independent.
yes, that's what I meant. So your time crystal is beyond that. I have nothing to say in the sense that it could be some kind of super radiant and time to time super radiant. There is no good theorem for that. That's my mistake.
As we're just educating all ourselves, when I'm teaching statistical mechanics, I tell students always that photons don't condensate. Or maybe they do, but why do I care? Because this would be zero energy, and if there isn't any particle of zero energy, they have to be held. It's just a mute discussion. Now, can you just summarize one more time for us what's so qualitatively different in a cavity that we can both condensate? Because there's always a statement, oh, photons is an antiparticle, and that way I can create many of the wishes, zero energy, and therefore I can condensate in the lowest state, right? That's the usual words that we all use when we do this. Is there anything that which aspect of these statements is now wrong?
The point is not, excitation are dress. So my basic entities are dress selection photon interactions. So,
yeah, the statement is if
macroscopic
photons were to
computations.
condensate, they would do so at zero energy, that's the lowest state. But I can get without any penalty have zero energy particle hole excitation that produce me 16 photons or 9, so there was no convention. Therefore, the whole discussion makes sense. Right? You're saying the cavity energy is finite. I think this is something important here. But,
I think there's something like that.
Yeah.
In this is where that constant dimensions to get zero energy, and then in the cavity it's got so I think there's something to do with the cavity being finite energy. That means it's some issue. But I can talk this stuff about maritime condensation. These things come up there. So what sort of gradients? What is it?
Yeah. Actually, definition of superradiance is very confusing from one place to the other. I don't think there is. Yeah. Mine is on the macroscopic occupation of the vacuum. But superradiance is a word which is used by many people for different things. And makes the whole literature very confusing. So that does not help, but is, yeah. If you see the word superradiance, you need some alarm. What does it mean? And that's not always the same thing.
I'm just curious why the notion of being in a ground state was inserted into the definition. I mean, definitions, you choose definitions to be useful. And so, what was the motivation for introducing the requirement in the ground state?
Could it be on zero temperature?
Historically, the whole formalism of coherent states was developed for photons.
Yes, sure.
So, which we of course use to describe the condensation of photons every day.
Yes.
You use particles, Savart points, everything else. So definitely the concept that was developed in the context of photons is used there in an everyday context by theoretical physicists doing condensed matter physics. And the entire setup of particles relies on Glauber's coherent states, which were inspired by photons.
Yes.
So we have no question that photons can condense into coherent states.
Yeah. Used for massless photons. Yeah.
Interesting discussion. Any final points?
discussion prompted a lot of changes attached. Right, so now
Yeah, share screen. Okay, no, it's fine.
Yeah, you are fine.
You don't need to all diagrams. Yeah, so the seven. If you take what experience,
I mean, tomorrow you want diagram? It's possible that
it could be all what experience, all diagrams.
yes.
Because I thought there was technically compared the memory function with single particle extension, which is a perfectly legal compared to Yahoo, but something that I would find only urgent if everything was dominated by single particle.
So we
right?
we took all the time when you're supposed to start.
Probably the second evaluation, yes, probably looking after that games on
I think we're going to restart.
for the
seven. Oh, yes, right.
That's why I mentioned the
I think
registration.
but certain entry also.
Yes, yeah.
We were nothing about 5 minutes.
Yes,
There's
I think just most
Okay,
so we're delighted this afternoon to have Wei Jing Chen, who's from the STM, Seamus Davis.
Sorry, I'm being polite. Thank you.
We'd like to start to have Wei Jing Chen, who's from Seamus Davis STM group at Oxford, and he's going to tell us some interesting new developments about the pneumatic pair density wave state in BISCO. So, thank you very much.
Yeah, thank you. Okay, today I would like to introduce our recent work on pneumatic pair density wave in BISCO 2212. Sorry. Okay. In this work, the experiment is mainly did by Mohammed Hamidian and Shen, Nair, and Wang Ping. They did the pre-analysis of the SATM data. And Seamus is the group leader, and Uchida and Isaki made the material. A striking feature of the underdog corporate phase diagram is the existence of intertwined order parameters. These order parameters, including CDW, SCW, pneumaticity, and superconducting order, and these orders. And multiple orders, multiple symmetries are broken by these orders. For example, CW breaks the translational symmetry, and SW break the time reverse symmetry, and pneumaticity break the C4 rotational symmetry, and superconducting break the gauge symmetry. A question. So question is there a parent state which spontaneously break these symmetries? If the answer is yes, this parent state can be the key to understand the phase diagram, and the many daughter states, partial symmetry breaking state, can be used as partially melted parent state. Here, the proposal is the pair density wave. Pair density wave states that that the Cooper pair carries the affinity center of the mass momentum. It is originally proposed for superconducting states under larger magnetic field serving the Zeeman splitting. And there are two solutions: the FF state, where the spatial modulation of the phase, and the with the spatial modulation of the phase and the constant amplitude, and the error state, with the spatial modulation of amplitude and the constant phase. A phenomenological theory of the pair density wave incorporated described by the GLW free energy density. Here are first the terms describe the first Hamiltonian described the intertraining of the different pair density wave order parameters, and the second Hamiltonian describes the intertraining of the PDW and the D wave superconductor. And there are several potential pair density wave ground states in this for this free energy density. The unidirectional and bidirectional FF type of state, and the unidirectional and the bidirectional LO type states. The important part of the proposal is that the PDW state may induce some other state by combining different PDW orders, PDW order parameters, and then they just here includes CDW, magnetization, density wave, loop current order, pneumatic order, and the charge 4E superconducting order, and these broken symmetry, the broken symmetries of these orders is a subset of the broken symmetries of pair density wave states. And there are in literature there are many theoretical proposals of the PDW's pair density wave incorporate, and also many experimental evidence have been found in this incorporate. So here, question: how can we directly detect the pair density wave in BISCO? The answer is yes. Here we use scanning adjustment tunneling microscopy, and we use a superconductor tip with if we can measure the adjustment current between the superconductor tip and the sample, then the adjustment current is proportional to the local density, local pair density of the sample, and because thermal fluctuation far exceeds the Josephson energy in our usually it far exceeds the Josephson energy. We are the junction is in the phase diffusion region, and the IV curve in the phase diffusion region obey this formula, this equation, and we can find this IM, and this IM should be proportional to the IJ square, IJ square in this function. Then we can get the local pair density. Here is our experimental proposal. Here is our experimental sketch, and we use a tungsten tip, pick a piece of BISCO from the surface of BISCO, and did the tunnel, Josephson tunneling between the BISCO tip to BISCO sample, between the BISCO tip and the BISCO sample, and because this BISCO tip is not a point, so it would like would work as a low pass filter, which would blur our image. And this is a typical topography in our experiment. Okay, let's start. The example used in this material, the example used in this work is BISCO 2212. The doping level is about 0.13, and sorry. Can I play this video? Sorry. Okay, escape the. Sorry.
Not sure.
Okay, play this way. Here, this is the IDV. There's a local density of the IDV map of this sample. We can see there is nearly no. We didn't detect any signal of the CT charge density wave in this in the material of this scoping. Again. This is Fourier transform of this image. And here and this is here is the topography of the HTM experiment, and this is the spontaneous measured IM map in this field of view. We can also find the zinc atom, which at which near the zinc atom the pair density should be suppressed near the zinc atom, and also the supermodulation in this image. After we did the Fourier transform, surprisingly, there are several points which have the periodicity of 4A0 of 4A0, and these are the signal of the pair density wave. Because previously we didn't detect any charge density wave signal in the DIDV map, so pair density is the dominant state in this material. And to separate the pair density wave signal from the original data, we use the two-dimensional locking method. Here we propose we propose the pair density wave have the amplitude changes in spatial amplitude changing and phase changing. Then using the locking method, we can extract its amplitude, spatial amplitude, and the spatial the phase. Now here is the result. Here is the result of the pair density wave in px direction and the py direction, px and py direction. And if we only pick out the amplitude, it's showing just two images. You can see the pair density, the signal paired, the amplitude of pair density wave is very disordered in the very disordered in our example. So, and they are we can also use the same way to low pass filter the signal near q equals 0, which is correspond to the disordered D-wave superconducting order parameter. And we can use which is A0. We plotted the A0 to x direction, then and averaged the PDW amplitude of PDW amplitude at each of the at the location where the average the PW signal at the location where A0 has the value indicated on the x-axis. Very surprisingly, it's different. Very surprisingly, we found they have a tendency that the PDW and the PDW and the superconducting D-wave superconducting order are attractive, and if we consider the GLW free energy model, their parameter should have this correlation. Next step, we also would like to check if there are pneumaticity orders, pneumaticies, and we define the pneumaticity order parameter as this this usually the in theory the pneumaticity order should only should be only defined by ax minus ay, but because our material very disorder, we normalize the ax minus ay by x plus ay. Here is the result. The red part is the px dominated region, and the blue part is the py dominated region. Actually, we can also see these dominant regions in original px pair density wave image and the and the original PY pair density region, the pair density wave region. Yeah, we can also cut the line profile to show these regions. These regions are actually dominated by the PX, and some regions are actually dominated by the PY modulation. So next question is, what pins the pair density wave? This was proposed by recent work in Brookhaven. They found that the zinc from their experimental data, they inferred that the zinc atom pins the pair density wave order locally. Then we can also find we can find the zinc atom in our data. Then in our data. Usually in STM, in the zinc atom would produce a local resonance peak in the spectrum in STM measurement. Then in our experiment, because we use superconducting tip, so it's the resonance peak of the zinc atom moves from minus 1.5 millielectron volt to about 20 millielectron volt. Yeah. So then we to show the zinc atom position, we calculate a Z map. Here is the zinc atom found on this zinc map. Then we map this zinc atoms, zinc sites found in this Z map to the pneumaticity map. You can see these zinc atoms are more likely to appear near the these zinc atoms would tend to appear near the domain boundaries, whereas shown as the black in this image. Okay. So in conclusion, we first visualize the pair density wave and the D wave superconducting order, pair density order in this in the BISCO 2212 near the with p equals to 0.17. And second, that we checked the intertwined we analyzed the intertwined PDW and the DSC order and found their amplitude are attractive. Then we calculated the pneumatic order and found a romanticity pair density wave state. Finally, we found that the zinc impurity atom site occurred dominantly within the domain war, pneumaticity domain war, which implies that zinc atoms pins the pneumaticity domain wars. Thanks. That's all my talk. Maybe too quick. Any question? Sorry. And thanks for yes, please.
Can you remind us this was above TC,
right? Sorry, it's under TC. So we have that D wave superconductor. Also have a D wave superconductor because we still need a very low temperature to do the SHM measurement at the present. At the present, because so that we can have enough energy resolution and have a stronger signal. This experiment is done at for about 50 millikelvin.
You mentioned that the density waves are pinned by the zinc disorder.
Yeah.
If you have samples with lower levels of zinc, do you find a more ordered pair density wave? Is there a sign of a more well-defined peak?
Actually, even there is no zinc atoms, there are it still has some domain. Has some domains. We haven't have we plan to do the experiment on some other examples in future. But currently we don't have the data. But because Shepard has a lot of previous work on the charge density wave, not the charge the density wave in the DIDB map previously, and they always can show the pneumaticity. So it can be so though I show the zinc atom pins the pneumaticity domain works here, but in this material, zinc atom is not the only mechanism which pins the domain wall, I think. Yeah.
And you've done it at 15 millikelvin.
Yes.
So you don't have any information about whether the correlation length is changing with temperature.
Yeah, we plan to do the experiment of the different dose. It's the different from 0.06 to here is nearly close to
your temperature remains fixed because you have to do the pair tunneling.
Yeah, I know we may, and I guess we are with the lower period. Yeah, 7 millikelvin temperature.
It looks more like a glass than a density wave.
Actually, the original proposal is that they believe this is proposal earliest proposal is made by Stevenson and Patrick. They believe they essentially give us a hypothesis that there is a long range due pair density wave at zero energy.
Yes.
If it's a perfect material, perfect. Yes. Yeah, but if there is a little disorder, if the disorder involved in the system, then this pair density wave would be melted to vestigial or some vestigial order states.
That's nice. Steve loves to make proposals that can never be tested experimentally. I don't think there's any way to test that, as far as I know.
Yeah, because we. The one thing we know is that if we decrease the doping, the domain size will increase. Based on previously DIDB data.
Yes.
Yes. But also because of the doping, disorder would also increase.
Yes.
So this might be due to the disorder. And we can't remove all the doping because if the parent material is extramagnetic, is a multi-exhibitor.
Yes. Yeah. It's amazing. Thank you.
Sure, please.
I have just a question on the experimental setup.
Yeah, sure.
When you have a very sharp dip and you want to make it dose,
yeah.
Here in tiny, and the temperature is about 8 K, but still, the problem is also that the charging energy is very large, and just because this is so sharp. So do you do something special? I don't know. Do you make a very blunt dip or something to do this scanning, or what exactly do you do to make that?
With charging.
Is there any problem? It works. I see it works. So I'm just asking, is there any problem, or what do you do?
Here we use the physical tube. Actually, the pixel and the next step we want to use the Niobium tube. I don't think, for me, I don't think there is the difficulty is that we need the tunneling joint must be very small. So we need a very small tunneling resistance about I think mega range. So this this code is required a very stable chip, and also our system should be very stable.
Are you doing these experiments at Oxford? Or
this experiment is done in Cornell.
Will you be moving the experiments to Oxford?
Yeah, I mean, this is what we want, what we plan to do.
Another experimental question.
Sure.
How do you build that? What exactly gives you sensitivity to the direction of the director in the pneumatic thing? show this nice color distribution. Just was that directly detected instrumentally or somehow processed?
You mean this one?
Yeah, right.
This is our original experiment data, the right side image. Then we can do the Fourier. When we do the Fourier transform, we found the two points of the Fourier density. Sorry, see. 2 points of Fourier density with this point. Yeah, we use the two-dimensional locking method to separate the Fourier density from the.
So yeah, so and I guess here the signal is just sensitive to the amplitude of your.
We can decompose both amplitude and the phase. Here we have both amplitude and phase.
The director only has a phase of pi. So that's
sorry, what there?
I mean, there's no arrow in the matrix, right? So up and down is the same.
Up and down. Sorry.
It's an axial object. It doesn't have a tip on the arrow.
Oh, you mean the tip shape or?
No. The magnetization has an up and a down.
Yeah. Yes.
And pneumatic does not.
Yes.
That's all it says. I'm just.
Oh,
yeah,
sorry.
Exactly. That's what I was saying. But then exactly my question was, how do you see that it's not an arrow? It's just a direct.
Arrow direct.
Does that come out directly from your data, or do you have to put in some theory knowledge?
No, I don't feel anything wrong. It's just directly use the two-dimensional locking method, and we can also directly do the low-pass filter. We pick up the Fourier component of this part, and of this point, this 2 point, then we can only filter all other Fourier component. Only leave this 2 point, then do the inverse Fourier transform, then we can also get the same image. Yeah, so it's because we accepted the locking method. We also checked with the more simple way to see if our method works. And it has both. Yeah, and if we here in this image there is a phase term, so there is both have positive value and negative value, and in this image I removed the only leave the amplitude terms, and this is the image of the amplitude terms. Questions?
Okay.
Thank you. Oh, maybe I need to change the. Yeah. Yeah, please. Thank you so much.
So what are you, HDMI?
Yeah, it's just his laptop. I think you should connect to that. Extend it to that screen.
Okay, extend. Oh no, sorry, not to extend. You can do simple. Duplicate. Sorry, I chose the wrong one.
That's fine. Okay. So for our next talk, we have Abhishek Prakash. He's also from Oxford. He's going to tell us about multiversality and unnecessary criticality in one dimension. Looking forward to it.
Thank you. I mean, both of these names are not inventions of mine. They're both by Senthil and P. So just putting it out there. Thank you for this opportunity to talk about some recent work I completed with Sid Parameswaran and Michele Fava at Oxford. It's titled Multiversality and Unnecessary Criticality in One Dimensions.
Oh, it's fun. Yeah, I like it.
So,
go ahead.
Sorry. So these are novel beyond Landau quotes, critical phenomena in a reasonably tractable setting. What they mean is as follows: like multiversality refers to a phenomenon where there are multiple universality classes on a single critical surface separating two phases. And unnecessary criticality is a phenomenon where one has a stable critical surface not separating any two phases within a single phase. So I'm going to provide a generic setting, meaning this is not a fine-tuned phenomenon. It's stable to a class of small perturbations where such exotic critical phenomena are observed. So the way I would like to anchor the discussion, at least to myself, is as follows. So this is a garden variety phase diagram. The phases, a phase diagram has two ingredients broadly: the phases and phase transitions. Characterizing both of them is a complicated affair. Like one needs to characterize the phase, symmetry, order parameters, out-boundary modes, response to gauge fields, things of this kind. Phase transitions, on the other hand, are classified by universality classes and characterized by the values of critical exponents, scaling operators, central charge of the theory, and so on.
These phase transitions are continuous transitions.
Yes, I'm only going to be referring to continuous transitions. So two seemingly extremely simple questions are: what is the relationship between these two ingredients? Meaning, if I say I have a certain universality class, can I say anything about what phases it separates? On the other hand, if I give two phases and then guarantee that there exists a continuous transition between them, can I say what the universality class between them are? And what I hope to convince you is that the answers to both of these questions is largely unknown, and as the examples I'm going to provide. So let me begin with the first question, which is: if I'm given a critical theory with a certain belonging to a certain universality class, can I say what the phases are? For example, if I have the Ising universality class, which I denoted as I, can I say what the surrounding phases are? There's one obvious example, which is if I take the Ising model and drive it to criticality, we know what the phases are. There's the Ising symmetry that's unbroken and Ising symmetry that's spontaneously broken. But we also know that the Ising universality class appears in separating phases as a transition between phases, which have nothing to do with any global symmetries. For example, if I couple the toric core with the magnetic field and drive the magnetic field beyond to a certain critical value, the system undergoes a transition from the Z2 quantum spin liquid to a trivial paramagnet through the Ising universality class. On the other hand, Kitayev's-Majorana chain, which separates a topological superconductor from an ordinary insulator, the transition also belongs to the Ising universality class.
Instances 2 and 3 dual to instance 1.
2 and 3 are in different dimensions, so I don't see how.
Well, okay, so but generally there's a say it's a chain. Well, generally there could be duality transformation, which brings you either one dimension or 2 dimensions to the corresponding even. I thought it's happening in cases 2 and 3. You can do a duality transformation.
Possible. Like you're saying, there's a way to argue that the phase transition in this model also happens to be a universality class, for which one uses dualities. But the fact remains that the phases are not characterized by symmetry being spontaneously broken. And that's the entire deal of.
I think you could declare a local symmetry being spontaneously broken.
No, I mean any symmetry.
Because I would say there is a Z2 symmetry until I call it spontaneously.
No, I think one can prove that the toric core phase is stable to any perturbations, literally any local perturbations.
Is that the same?
Sorry? Is that the same
as there being no symmetry, even for non-local?
Yes, if I can explicitly break symmetry and the phase is stable, there's no symmetry being spontaneously broken.
Carry on. We're going to have a good discussion.
Yeah,
sure.
I don't understand what is criticality here? I mean, if I measure the heat capacity, right, I would expect the exact same result for the ketide marijuana chain and for the transverse field Ising model. If I measure, this is one critical exponent. Another critical exponent, eta, measures correlation functions of operators with local support. And there I can tell the difference between these two objects very well.
What two objects?
Oh, between a state that has an order parameter or a state that is a topological transition. So these are very, very different states from that perspective.
I agree with you.
What do you mean by criticality now? What is the object that we are supposed to look at to say these are the same, I can't tell the difference, or these are different phenomena?
I mean, that's a big question, but a limited answer perhaps is that there is a critical theory defined by conformal field theory, where there are scaling operators, anomalous dimensions, and so on. We could assign symmetric charges and then actually detect where this is coming from.
Yeah.
But if we consider the data to be scaling operators, critical exponents, and things of this kind, I would say they're the same.
Let's measure the spin correlation function of the ketide chain. I get the exact same result in the spin correlation function of the Ising model.
So I didn't get the question though. I agree with you. Yes.
I don't think so. You do get the result.
Sorry?
It's a very different objects. One is it's a non-local representation of the other object. So they should give me very, very different results. The spin correlation function of the ketide chain is non-interesting and yet, and one of the Ising model is clearly.
No, I think I'm not clear about what the question is, because indeed there are operators which have exponentially decaying correlation functions, and in one model, and there are certain operators which don't. But the critical theory is identified by what operator maps to what operator. For example, if I have one scaling operator that comes from the Ising model, then I can map it onto the scaling operator that comes from the ketide chain, then that's basically done.
I think we should let him go on. We'll have a good discussion afterwards.
Well, my point being, and we could discuss whether you agree with this, is the universality class does not tell us what the phases surrounding are. This was supposed to be an example for that.
I disagree.
Okay, that's even better. Okay. Well, you don't need to take this example. Our example should also work. So there's a converse question, which is, if I tell you the phases, can you tell what the universality class is? And here the answer was supposed to be, it's considered to be more unambiguous, in the sense that if I have the Ising model and symmetry is spontaneously broken, I know we get the Ising universality class. That was the assumption generally. And of course, there are some caveats. For example, in this diagram, as long as I tune one parameter, there's a universality class. But if I tune multiple parameters, we all know that there are there's multi-criticality, and that could be a different universality class compared to the original one. So, for example, IAB can be different from the center point, which is IABC. Although this is generally considered to be true, meaning that if I have two phases, the universality class of the phase transition separating is uniquely specified. If this is considered to be true, there's actually no fundamental reason for it to be true. And in fact, I'm going to provide counterexamples to this. The counterexamples that I'm going to be providing are as follows. These two phase diagrams are supposed to be counterexamples. The first one has two phases, which is a trivial paramagnet and a symmetric protected topological phase, where the critical theory has multiple universality classes. And I just labeled it by the central charge of the critical theory. And that changes without any change in the surrounding phases. A second one is a critical theory that's not even associated with any phase transitions, because it's a finite critical surface that abruptly terminates lying within a single gap trivial phase. And the rest of the talk is going to be about models that actually give you these phase diagrams. Let me mention that this phenomenon was postulated to exist by Senthil and B in this paper, which was published in PRX in 2019. Their setting is a bit more complex. They consider 3+1 dimensional field theories with non-abelian gauge fields belonging to the group, symplectic group with NC colors and coupled to large number of fermions, which are transform as a fundamental representation. They postulate that this field theory, which produces diagrams of this kind, emerges from some microscopic model. Our setting is relatively simpler. They're 1 + 1D spin ladders and or coupled lattice liquids, and many things that are not accessible in the original setting are also accessible, and it's also easy to verify them analytically and numerically. So let me begin with the first example. So the model is relatively simple. It consists of 2 copies of the XXZ chain with bond alternation, alternative bond strength. One important detail is that the ZZ coupling, the ZZ coupling, is negative, which should be ferromagnetic coupling. This is an important requirement. And the vertical coupling, the rung coupling between the ladders, is a simple ZZ coupling. I'm going to be charting phase diagrams by varying the vertical coupling JPerp and the strength of bond alternation. The phase diagrams are going to be 2-dimensional, and these are going to be the axes of the phase diagrams. All right. So before, I'm going to explain why this phase diagram is. This is the phase diagram of the model. Let me first start off by listing the gap phases, and these are easy to determine analytically by going to the extreme dimerized limits and switching off the layer coupling, the ladder coupling. So we have in one dimerization limit, we have with a particular choice of the unit cell, which is this 4-spin unit cell, which is natural for a translation symmetry, explicitly broken Hamiltonian. The Hamiltonian takes support only on these bonds, and the ground state is easily obtained as singlets that live on these bonds. This is a trivial paramagnet, which is a product state. And any kind of vertical coupling, the ZZ coupling, does not really change this. It's stable to small couplings. Now let me go to the opposite dimerization limit, where the Hamiltonian takes full support on the bonds in between unit cells. The ground state is once again easily determined by putting singlets on these lines. And this is a caricature of a symmetry protected topological space. One way to see this is there are, at least in this representation, there are dangling qubits. There's a 4-fold degeneracy on each end coming from 2 spin-a-halves. And it's easy to check that small amount of coupling, ZZ coupling, does not eliminate the boundary modes. It lifts the degeneracy from 4-fold to 2-fold, but this 2-fold degeneracy is protected. There are many ways to argue this, but this is the simplest explicit way of checking it physically. So these are the 2 gap phases. Now the question is what happens for 0 dimerization, which I claim corresponds to phase transition. So for 0 dimerization, we have 2 decoupled, at least for no coupling between the ladders, the legs of the ladder, we have 2 decoupled XXZ chains. And for the choice of the parameters, they belong to the gapless lattice liquid phase. So we have a C = 2 conformal field theory that labels the transition. Now, the question we have to ask is what happens to this decoupled Luttinger liquids in the presence of interactions? And the best way to do this is bosonize the theory and then study what happens to these perturbations in terms of how relevant they are. So this is easy to do. We can bosonize the decoupled Luttinger liquids in terms of the 2 XXZ chains in terms of 2 decoupled Luttinger liquids. For our choice of ferromagnetic coupling, the Luttinger parameter takes values between 1 and 2. The interactions, the vertical interactions, come in the form of 3 operators. There are 2 vertex operators, cosine potentials, and 1 exactly marginal operator. The question of what happens to this C = 2 critical theory reduces to whether any of these operators are relevant. So this is also, there are standard ways of checking this, and it turns out that at the origin, for no coupling, both the vertex operators are irrelevant. So they don't change the C = 2 nature. It continues to be 2 copies of Luttinger liquids. So there's a small region around the origin where the C = 2 nature continues to be stable. But as we increase the value of the rung coupling, the scaling dimensions of these vertex operators are changed. And here's a perturbative result, which we can also measure numerically. We don't need to rely on this. This holds to some extent, but what this tells us is that at some point, for some critical value of the rung coupling, one of the operators becomes relevant and reduces the C = 2 theory to C = 1. So there's a change in the critical theory from something which has central charge 2 to something which has central charge 1. And my claim is that when this happens, the gap phases remains the same. Now that's a non-trivial fact. For example, this is a possibility. Right? It could be that the critical theory changes, but of course that could also mean that the gap phases are also changing. And what we have is a complete ordinary phase diagram. And this is actually easy to check. First of all, we can check this numerically, and this is not true. And it's also easy to check using Bosonization by seeing that the Bosonized form of the dimerization operator and the Bosonized form of the vertical coupling, their energies are minimized by the same field configurations. They're compatible, so they don't frustrate each other. And it's easy to see. Like, when phi1 and phi2 becomes pi, 2 pi is also the ground state of the H purple. Things like that. So the C equal to 2 and C equal to 1 theories are critical segments on the same surface that separates two fixed phases. So what we have is a phase diagram of this kind. And this is a one-dimensional example of what B and Cynthia call multiversality. And if you don't believe the first example, this is a clearer example of how universality class doesn't tell us phases because it's not unique. Yeah, sure. Maybe that was a poor example. Of course, this model is simple. So unlike 3+1 dimensional gauge theories with large number of layers of fermions, this can actually be tested numerically. And here I've shown a simple plot of how the central charge changes as we go with JPERG. And this matches exactly when one of the operators becomes relevant. Before I move on to the next model, let me pause here to see if there are any questions. Or I can also hold out till the end of the talk.
Is there any boundary that extends from the C+1 to C+2 phase transition?
What would you
You've got purple region separating the two green lines. Like a diagram.
Yes.
The dot, you've got the dot there.
Right.
Point that goes from C+2 to C+1. Is that just a point, or are there lines that come out from that?
No. So yeah, I mean, I think this. You mean like this?
The question mark. Probably.
Yeah, there isn't. So we can check this numerically, and through Bosonization, we can argue that there isn't any line. And the dot, it gives you an impression that there's something special, but no, it's just an ordinary KT transition.
And if I were to go a little bit to the right of this line,
which line?
So you have the vertical line, that is your phase transition. But I want to go now into the ordered phase.
Right.
Now I'm going vertically up.
Right.
Do I sense in any way by, for example, changing critical amplitudes, not so much really critical exponents also, do I sense these transitions from C+2 to C+1 somehow in the ordered phase?
Well, I mean, the simple answer is if we have access to long distance correlation functions, yes. But if you're very close to the critical line, depends on how far away we move. But if you have access to long distance correlation functions, we can see that some of them, which were previously algebraically decaying, and we can tell which operators these are now exponentially decaying. So what used to be scaling operators in the C=2 theory are no longer scaling operators. Numerically, of course, they're limited by system sizes, but in principle, yes. All right, so that brings me to the end of the first of the two exotic phase diagrams in quotes. The second example is very similar to the first, in fact, somewhat simpler. One important claim is that this phase diagram we claim is unchanged in the presence of small symmetric perturbations. So we can provide a sufficient collection of symmetries, which if it's preserved, any operators with small coupling constant does not change the nature of this phase diagram. So it's not a fine-tuned phenomenon which requires tuning multiple parameters. So the symmetries that are sufficient to preserve this are an independent U1 spin rotation on each layer and a common spin reflection symmetry, as well as a layer exchange symmetry. So these are, as long as we preserve the symmetries generated by these three generators, spin rotations, spin reflections, and layer exchange, it's easy to see using Bosonization that all of these things go through and nothing is going to change. That's right. These symmetries also protect the topology. It also protects this phase diagram. So it protects more than the topological phase. So this is necessary to preserve the phases. If we break too many symmetries, for example, the C=2 shrinks to a point. So it involves both the phases and the transition. So as I said, this is sufficient. Maybe there's a way to enumerate the rules of what is sufficient, but what is necessary that I haven't figured out. So the second example is a small modification of the first, which is we consider the two copies of XXZ spin chains with alternating bond strengths. And instead of a simple ZZ coupling, we use an XXZ coupling. So we're going to study the phase diagram of this model. Also, one extra detail is that we force the vertical ZZ coupling to be less than 1 in magnitude. And that's the only requirement. Apart from that, we're going to chart the phase diagram with bond alternation and the J-perp coupling. So these are the phase diagram in these two parameters. So I claim that the phase diagram for the model that I wrote down looks like this, the 2D phase diagram. So let me first argue that there exists a single gap phase, no more. And this is easy because there are limits where we can track the phase diagram exactly. So let's start off with one extreme end where the Hamiltonian is completely dimerized and has support on legs that couple unit cells. The ground state is obtained by putting singlets there. And this looks like a symmetry protected topological phase with boundary modes, but these boundary modes are accidental. Any small amount of J-perp eliminates the boundary modes. And in fact, if I take J-perp to infinity, the Hamiltonian takes support on the vertical legs, and the ground state is obtained by putting singlets on these vertical legs. And it's easy to check because it's a 4-spin Hamiltonian that there's absolutely no phase transition. You can just ramp up J to infinity, and we go from singlets that are horizontally aligned to singlets that are vertically aligned, and there's no phase transition. At this point, the Hamiltonian has no parameter, there has no coupling to the dimerization operator. So I can go, So I can go all the way to the other end of dimerization with absolutely no change in the ground state because the Hamiltonian has no dimerization in its parameters. And now I can reduce J-perp and come all the way to the trivial phase when the ground state once again realigns from vertical to horizontal. Now it's a completely product state. So we went from the SPT phase all the way to the right, or what we thought was an SPT phase, and came all the way to the trivial phase without encountering any bulk phase transition. So we can also do this and go all the way back from the lower half plane and then show that this entire phase diagram in the periphery has a single gap phase. Right? So now the question is, what happens to the origin? Once again, with no bond dimerization, we have a C equal to gapless theory. Right? And we want to understand what happens to this gapless theory in the presence of the vertical coupling, the perturbations. Once again, we bosonize this. Once we bosonize it, in the perturbations, there's an extra player in the game. So we had two vertex operators similar to the case before, an exactly marginal operator which changes the scaling dimensions. But now we have a third vertical operator because of the new couplings vertically. So cos theta 1 minus theta 2. Theta and phi are dual variables in the usual way. It turns out that while cos phi 1 minus phi 2 and cos phi 1 plus phi 2 are not relevant, cos theta 1 minus theta 2 is relevant in the standard way that typically C equal to theories are unstable, and this thing gaps it out. So it reduces immediately the C equal to 2 theory to C equals 1, a single component Lagrangian liquid. But it turns out that this one is stable until we hit a critical value of the vertical coupling. So there's a stable C equal to 1 line that abruptly terminates to adiabatically connect to the single gap trivial phase. So that's that. Once again, all of this can be verified using bosonization, but also easily verified numerically using DMRG. And I once again shown the plot where we can see the change in the the central charge as it goes from 2 to 1 to 0 and connects to the single gap phase. So this phase diagram consists of a stable gapless surface, critical surface, separating a single phase. And this is why I suppose Senthil and B called this unnecessary criticality. This is stable to a less restrictive collection of symmetries, this phase diagram, as long as I preserve spin rotations and spin reflections, which forms an O2 onside symmetry, as well as a layer exchange. Just these two symmetries are sufficient to guarantee that this phase diagram is stable to small symmetric perturbations. Right. One final thing is the model, the simplicity of this setting gives us access to features that are hard to understand in the complicated field theory setting or central line P, which is we can find out what happens when the the universality class changes. Here, it's easy to see that it's an ordinary KT transition. In fact, we can also list a sufficient collection of ingredients for phase diagrams of this kind. We need a single relevant operator that gives us the gap phases and a marginal operator that drives the change in the critical surface with some extra ingredients. This can easily be generalized from 2 legs to 2n legs with an appropriate modification of the symmetries. And also we can generate other examples, porting our knowledge from the classification of SPT phases and things like that. So I'll end the talk with a few questions that I don't have an answer to, which is what exactly, how do we construct, like, systematic, what are the necessary ingredients for universality class changing, and whether there are realistic settings where this can be seen. And the big question, which I really have no answer to, is why are such phase diagrams so unusual? Like, why is it that it took 2020, like 2019, to come up with examples where such things do happen? That's it. Thank you.
I have a question. Just roll things off. Do your phase transition phase diagrams have a finite temperature analog? Namely, it's in classical static models.
That's a very good question.
Do you know?
Yes. So there are examples where the 2D classical mechanical models, where indeed the only paper I've seen is by Paul Fendley and Austin Lamacroft and a third author I can't remember, unfortunately, where they have a KT phase transition to an Ising universality class. And this is a purely classical mechanical model, 2D static.
Can I just make a thought that actually your extra sequels 2 phase in the first one and your unnecessary criticality in the second one are basically from the same origin.
That's right. I agree. Yes.
Based like within the bosonization, you have 2 modes within this first phase diagram between a topological insulator symmetry, a trivial insulator symmetry protected phase. Only one of them needs to change. But then the second one just happens to go to 0 as a kind of accident or an unnecessary thing, because the operator just isn't there at some limit delta equals 0. And in the second one, you have exactly the same thing. That operator just isn't there, which is why you get the extra criticality.
That's right.
So it all comes from actually the same origin.
My examples, yes.
In these examples.
Yes.
Okay, but
yeah, I agree. Yeah. It'll be nice to find out if there are other settings also. This is what I could do.
Yeah, sure.
Other questions? Okay. Within formal discussion, I think, and let's close today's activities. Thank you very much. I think we will continue tomorrow at 10 o'clock.
I think these examples, you can sort of say, if you know these 2 phases, you know the criticality between them must be at least this. The central charge will be something, but there might be more by accident.
I mean, the word accident is stable to find in the perturbations. And there are other examples where